Okay, hi everyone. Thanks a lot for joining us. Thanks a lot for joining the workshop on Frontier AI in Cybersecurity, Risks and Opportunities. So now we'll start the workshop. So first, I will give a quick opening remark. My name is Danzig. I'm a professor in computer science at UC Berkeley and also a co-director of the Berkeley Center for Responsible Decentralized Intelligence. And it is great to welcome everyone to the workshop. And the workshop is co-organized by the Berkeley Center for Responsible Decentralized Intelligence, RDI, and also Schmidt Sciences. So we are all excited about the fast advancements in Frontier AI. The Frontier AI capabilities has been increasing really fast. And also this year is called the year of agents. And we've seen an really impressive explosion of AI agent development as well. And at the same time, we also need to be aware of different types of risks as well. In particular, I do personally believe that cybersecurity will be one of the biggest AI risk domains for a number of reasons. Today, attackers have diverse incentives for attacks, and today attacks are already causing huge damages. And increased AI capabilities can significantly reduce attack costs and increase attack scale. And cyber attacks and defenses are complex. So for example, for a successful cyber attack, oftentimes it goes through multiple stages in the kill chain. And a key question is, how will frontier AI change the landscape of cybersecurity? Given that AI is a dual-use technology, it can help both the attacker side and the defender side. So a key question is, who will AI help more, attackers or defenders? And why are we hosting the workshop now? So from what we have seen, AI agents are now reaching a breakthrough moment in cybersecurity. So for example, from our recent work, such as benchmarks, like CyberGym and Bounty Bench, and also together with other results, for example, from recent results from the AIxCC Cyber Challenge, we are seeing the rapid advancement of AI capabilities in cybersecurity and seeing that AI today can meaningfully support many different types of real-world cybersecurity tasks. Here is just one example of our recent work, CyberGym, which develops a new benchmark that includes close to 200 large-scale, widely distributed open source software. And this open source software contains over 1,500 previously discovered vulnerabilities. And we task AI agents with two main tasks. One is to try to detect these previously known vulnerabilities. And the other task is to identify previously unknown vulnerabilities, also called 0 days. So from the CyberGym benchmark and evaluation, it demonstrates that frontier AI's capabilities in cybersecurity is increasing drastically, especially with the most recent model releases. For example, Sonnet 4.5, the AI agents can identify close to 30% of previously known vulnerabilities in the benchmark with a single trial. And also our agents have been able to identify 35 0 days in these large-scale, widely distributed open source software. A number of CVEs have been issued from our discovery 0 days as well, and also developers have patched a number of these vulnerabilities also. And also CyberGym has been included in the system card for the most recent model release, Sonnet 4.5, from Anthropic. And Anthropic's work also shows that as they increase the budget for agents, this also allows the agents to significantly increase the vulnerability reproduction and the discovery success rate. When they increased the trial to 30 trials instead of a single trial in the CyberGym benchmark, the agents were able to actually identify close to 67% of previously known vulnerabilities, and also discovered significantly more new vulnerabilities as well. So all these recent findings demonstrate that AI capabilities in cybersecurity is increasing drastically. So this poses a number of key questions. So first, how is frontier AI is being applied across different stages of the cyber security landscape, including both the attack and defense side? Second, what lessons can we draw from real-world benchmarks and deployments today? And more importantly, what milestones or breakthroughs will signal that the AI systems will substantially change the cybersecurity landscape and the balance between cyber offense and cyber defense? And how would we together prepare for these tipping points? And more specifically, what concrete steps should stakeholders take, both for near term and longer term, to build resilience, close the evaluation gaps, and ensure safe and beneficial uses of frontier AI in cybersecurity? And finally, how can academia, industry, civil society, and government together to work together to better coordinate, to anticipate risks, and leverage the opportunities to really build more resilient society to enable us to benefit from frontier AI while at the same time mitigate risks in cybersecurity? So with that, we'll welcome everyone to join the workshop today. We are really glad to see that about the huge excitement about this workshop and the importance of this topic. So we have over 2,000 registered attendees for this workshop. And in this workshop, we will hear presentations from AIxCC winning teams, leading researchers from frontier AI labs, academia, and also leading tech and security companies and governments as well. And our workshop has two parts. Part one is today, and part two was originally planned to be on November 12th, but due to government shutdown, a number of speakers are impacted for the part two dates, and we'll announce the new part two dates after the government reopens. With that, thanks for everyone, and hope everyone enjoys the workshop.
Thanks, Don, for the opening remark. I'm Wenbo. I will be the moderator for session one, which is AIxCC. A little bit of background, what is AIxCC? It's the cyber challenge, grand challenge that hosted by DARPA. It's been hosted for 2 years, since 2023, and then the first year is from like the initial phase to the semifinal, and the second year is from semifinal to final. From semifinal to final, there are 7 teams competing in the final for a year. In the competition, the team need to build the AI-driven cyber rating system that automatically identify and patch vulnerability in real-world softwares. Today, we are very happy to have the team lead and the core member from the top 3 teams, which give us presentation about what they build and share their experience. We'll start from the winning team, Team Atlanta. Very happy to have Professor Taesoo came from Georgia Tech. We also the leader of Team Atlanta share with us the experience and the cyber rating system they build. Yeah, thanks.
Okay, this is Taesoo Kim. I'm Professor at Georgia Tech and VP at Samsung Research. Today I'm going to tell you about hyperscale bug finding and fixing in the context of DARPA AIxCC and our team, the Team Atlanta. My research area in traditional security area, security research. For example, we are doing automatic bug findings, and also write exploit against them. But lately, all the research that we are doing is extended by LLM. Even writing exploitations, we heavily leverage LLM in terms of synthesizing exploit primitives to achieve remote code executions against target software. We are very much grounded teams. We show our capability of writing exploit and defending through various competitions, such as DEFCON CTF. We also won one-to-one competition in a way that we can demonstrate remote code executions against Apple Safari and macOS in the past. Unfortunately, though, I'm far from AI persons. I hope that today's takeout from my talk is all about a security expert's take on LLM to solve domain-specific problems, and how powerful it is to leverage AI when solving your security problems in your hand. But in the context of DARPA AIxCC. DARPA has been organizing lots of grand challenges before to address societal problems. Self-driving car, or also known as urban challenge, is pretty well known to public. And there was a humanoid robot competition to develop humanoid robot for the rescue missions. And a few years back, there was competition called Cyber Challenge. The goal of CGC is all about creating autonomous agents that can attack by writing exploitation. And each of those grand challenges after several years sparked huge industry. For example, it's very common to see Waymo and self-driving car on the road. And we now see huge competitions in robotics, humanoid robot development right now. And after CGC, many of the big companies start adopting fuzzing as a main way to evaluate their security for their software product. DARPA AI Cyber Challenge has been announced in 2023. The aim of the competition is to protect and security critical cyber infrastructure in the United States. Now, what is AIxCC? It's a competition to design autonomous systems, or called cyber reasoning system, that can find and patch the vulnerability from the open source project. So one of the core idea of AIxCC is to scale a traditional software analysis techniques that actually work against the real world software, like Linux kernel, in that scale, so that we can actually find the vulnerability from open source project at the end. This is not just interest from government and academia. It's actually backed by many of AI companies like Anthropic, OpenAI, and Google and Microsoft. And the competition is announced in 2023, but semifinal happened last year, and final happened just a few months ago. And the total amount of stake as a total prize is actually $30 million. Means it's a very serious competition at the end. And semifinal happened a year ago in DEFCON. What's interesting here is that 42 teams competed for the semifinal. Only 7 teams proceed to the final. And we had to analyze Linux kernel and Nginx and Jenkins and SQLite. This is a large scale application with a very limited budget. But what's interesting in this competition is that there are 3 large groups of people competing for a semifinal. Some people bringing their AI tool, rooted from AI community. There are another group bringing their PL or software engineering technique. And there are security folks who are experts in security area, but they want to tackle the exact same challenges by bringing their expertise. But at the end, all the 7 teams, and most of the 7 teams are grounded in the security area, which indicates that solving their domain-specific problem by leveraging all recent advances in AI is critically effective at the end. I'd like to give you a little bit of taste of what type of challenges we have to solve in semifinal. This is one of the exemplar challenges from Linux kernel. And in transparent enterprise communication layer, shortly TIPC, when 2 processors are communicating each other, you can create a session key. So when one process initiates the session key, and this is the function that is invoked inside the kernel. And one processor should package everything as one message and send to the other end. So inside the package, there are size fields that represent the total message that you're sending. But at the same time, user can indicate amount of size byte that is related to the data inside. So in other words, the entire allocations happen in the entire message size, but attacker can provide the longer size input for the data they're gonna send inside. This is basically K input. And then they can override beyond the allocated amount, which is a simple out-of-bound memory write happening in this source code. But think about the AI-driven approach, given LLM, how to find such a vulnerability. The Linux kernel alone, we have 30 million lines of code, which is almost impossible to analyze this huge repository by merely tackling everything in a static way. So one of the interesting decisions made by organizer in order to solve this fundamental challenge is to provide harness. You can think of it as a fudging driver that drive the entire interaction or govern the entire interaction from the user input. So this, in the context of the Linux kernel, you can think of a user-space program that interact with the Linux kernel with a very explicit step. And your job is to find the bug triggering input that can inject to the user space program and use it to program by interpreting every single field in the data that you provide and ultimately drive the execution to the buggy locations and trigger the vulnerability at the end. I think I'd like to highlight the differences between tackling this in pure static way and the proof of vulnerability that we care, which is very critical in terms of reachability analysis. If you analyze this entire source code with CodeQL like static analysis tool, and they typically create the big warning against the kmalloc area. So size fields of kmalloc is basically 2 bytes in this case, but unfortunately it's a very error-prone decision because once you allocated 2 byte size with like 4 byte or 8 byte argument of the kmalloc, is pretty much error-prone in terms of overriding what fields that you're going to override the buffer area after allocation. But in fact, this is actually not related to the bugs that we are analyzing in this source code. The out-of-bound memory override happening in the last line in this code snippet. But most of the static analyzer, we just complain this allocation side with the smaller byte as an argument to the kmalloc. In fact, this also indicates the importance of those criteria in real world. This is coming from one of the open source projects called Curl, and immediately after LLM become popular, and they are effectively DOS by the huge number of bug reports. But according to their practice, because the bug report is so convincing, they have to spend ridiculous amount of time as a developer to understand and validate whether the report is actually correct or not. But at the end, most of their time is actually wasted. So in other words, when you're writing cyber visioning systems, providing the input that actually trigger the vulnerability by solving the reachability problems is significantly important. Probably the most important criteria as a security tool that we care in AIxCC and general bug finding tool. And what counts for security task in AIxCC? There are 4 different tasks. One is the proof of vulnerability, basically generate the bug triggering input against the target software. And you also have to fix it by generating patch. And also there's an interesting new security test called Sheriff assessment, meaning that given a report from static analyzer, you have to validate whether you have to decide whether this report is valid or not. And also there's an additional security test that connect the POV to the patch or Sheriff report all together so that you can relate them at the end. And you have to perform 4 different security tests in 2 different modes. You can perform this entire security test on entire repositories called full scan mode, or you can apply these 4 different tests in the context of the new commit the developer create. You can think of this actually reflect the real world development paradigm. You create a new patch, say feature patch against the software, and this particular patch likely contains the vulnerability. Instead of scanning the entire repository, we like to perform security tests against those code regions, which called data scan in AIxCC. Final happened in DEF CON a few months ago, and this is a visualization of the competition. Unlike self-driving car, we don't have many things to visualize. Each of the team is competing in this space and just invoking LLM to the top purple side is the external LLM call. And you can also see the complexity represented as a sphere in the green side. And basically all the sphere is a green circle at the end because of the complexity of the software we analyze. And I'm proud to announce that our team member, Team Atlanta, won the competition. We got $4 million cash prize from the DARPA competition. In total, got $6 million as a whole. But one thing I like to highlight is the actual end scoring. Our system achieved more or less same score than two other teams combined. And the rule is pretty interesting. And we also outperform most of the category of the security test. And the rule is pretty simple. They assign a static number to each of the security tasks, but there are interesting accuracy multiplier, meaning that if you make an incorrect judgment call and you make false positive, basically, then your score will be deducted with following this rule. So in terms of accuracy, because of accuracy multiplier, and in fact, this is a realistic challenge from the real world, we make tons of conservative decisions so that we can maintain high accuracy score in this competition. In the final, we analyzed about 28 real-world open source projects that include systemd and Crow and libpng, which actually back everyday software stack that we are using. In total, all the team had to analyze about 70 vulnerability out of 28 repository. We could take about 77% overall team. And out of 54 vulnerability that we identified, we could also fix about 43 vulnerability at the end with a time frame of 45 minutes. What's interesting in the competition, your task is not just finding synthetic bugs in the open source project. You can also find zero-day vulnerability. In fact, in the semifinal, our team is the only team who discovered the zero-day vulnerability in the SQLite. And the final, we discovered about 6 vulnerability by our team and 18 vulnerability total by entire team combined. This is another interesting number that you can see. The total amount of computing spent, with including cloud and LLM resources, our team spent about $360,000 at the end. But if you divide this entire amount that we use in total by the amount of security tests that we have, this is the final number. It means given a random repository, the random open source project in larger scale, this is the amount that we can initiate the pen testing or security auditing. In fact, compared to human auditor, typically takes weeks and months. This is a ridiculously small amount of money. In fact, if I over-exaggerate a little bit, this is the amount of money you can initiate the pen testing against the new code. And we now see huge possibility of automating all this process through AIxCC. And I'm happy to talk about our approach of Team Atlanta. So when we start this entire competition, when we start preparing this competition, like any other domain experts, we thought LLM is not ready. We started as AI skeptic for reasons. We evaluate all the commodity LLM services outside. Per our evaluation with the benchmark that we designed, none of them actually work properly. And discussion at the time is very primitive. We talk about chain of thought and tree of thought and self-consistency. And even people start discovering some tips, some tricks. Say, hey, if I say I'm going to tip a beat in prompt, and people start realizing that LLM actually respond with the longer response, for example. And there are tons of discussions in primitive level. For example, hey, what's the right way to represent source code inside the prompt? Hey, what's the right way to represent line numbers? Hey, do we need a bracket or semicolons? And what is the right way to generate the patch? And should we just ask to generate the diff? Or what am I just to rewrite the entire function so that we can generate the patch at the end? And these are the extremely primitive discussions, but these are very important subject at the time because LLM is merely ready in the time frame. And importantly, context windows seem to be very primitive, and we also realized the fundamental problem. And there is a huge race going on in enlarging the context window at the time. We start seeing the 1 million context window announced by Gemini, but unfortunately, committee also realized that even if you have a larger context window, depending on where you locate the needle, and the accuracy of or performance of an entire agent different. So in other words, still, it's very critical to maintain the usage of context window small in order to make your agent work effectively at the end. But at the same time, we start seeing some of very huge potential. What's interesting here is that instead of asking LLM to answer the questions that you ask, you can ask LLM to generate the code that can answer the question that you ask. This is a pretty interesting paradigm shift at the time. So that code interpretation became very popular. Now we implement it in our team. We're going to have a proxy layer that implement custom function code that support every single LLM provider, which become more or less obsolete these days. Many of the LLM providers lately provide the native support for the function call and callback and name. We also see a lot of development happening in software agent side. The OpenAI is very popular, and we heavily leverage those agent architectures in our semifinal. But unfortunately, though, we couldn't fully leverage the LLM breakthrough at the time because we have a limited time and resources. But for the patching, we extended the ADAR and SW agent in a way that we can focus on the specific type of vulnerability in generating patching. For bug finding, we apply the idea of LLM in the loop so that we can replace some of the human efforts by using LLM. For example, when you're generating C to accelerate the performance of fudging, we heavily leverage the LLM for the semifinal. But after semifinal, everything changed. We now see that context window is not the problem anymore because of new technique like summarizations of the chat history or there are a bunch of compaction techniques. And we can also design the agent in a slightly different way, like sub-agents and multi-agent, in a way that we can effectively utilize the context window in the given commodity LLM. We also start seeing some modern breakthrough in agentic architectures. Like now we have Cloud Code and Codex and Gemini, which happened in the middle of the competition. We actually try to understand their design decisions by reverse engineering and many things behind the scene. We actually adopt many of their design decisions in our final implementation for the final round as well. In Atlanta TRS for the final competition, we adopted LLM everywhere. We have a proxy layer that abstract every single interaction for the supported LLM provider, like Grok, for example, and Gemini and whatnot. Not only that, every single agent that we develop heavily utilize LLM for the bug finding and patch generations and sheriff analysis as well. I'd like to highlight some of the key principles that we adopted when designing CRS. In fact, if you see our CRS design, we have 3 separate agents running concurrently to find the vulnerability. In fact, this is a popular idea in system community called M-versioning for tolerance. And we also made tons of orthogonal design decisions among, so that even if one system fails, then other systems start interacting with the organizer's competition involvement. But at the same time, for C and Java, we still prepare tons of traditional tools, like ensemble fuzzers and concurrent executor and directive fuzzer. These are not as sexy as it sounds for AIxCC, but we still believe that these are very important subject tools that we have to utilize for better accuracy in bug finding. I'd like to highlight some of the decision here is that when you're generating new input through LLM in the process of fudging, the simple idea is that you can ask LLM to generate, or you can ask LLM to mutate given input. But this, because of the property of LLM is extremely slow, the end-to-end latency of LLM takes 30 seconds a minute. It's extremely hard to leverage it. And instead of asking LLM to generate the final input, we ask LLM to generate the code, which can cover the huge amount of input space for the target program. So we can ultimately saturate the fudging process through this design decision. And standard fudging has 4 different steps. You have a scheduling step that selects the input, and you do the mutations and run the fudging execution with the mutated input. You're going to update this process. But standard fudging is really tailored for specific program languages. And many of those small components require specific extension of the program languages. But in our CRS component called Atlanta Multilang, we actually implemented everything. We abstracted everything with LLM in a way that we can perform fudging in language agnostic manner. Our system is actually very complex, but I'd like to highlight one of the components here, what we call test-line-based agent. So given a source code, our agent try to create the grammar by starting from the entry point of the harness and navigate the entire source code base. And at the end, it produce the grammar, potentially correct grammar, in a way that instead of doing random mutations against the target program, we can actually respect the type constraint against the input to the target software. The patching agent is all about LLM. We implemented six different agents in our patching agent. We ensemble them together. This idea is pretty interesting because you don't have to develop one agent that work universally well across all these bug types. Instead, you can develop a very specific agent that only work for a certain bug type. But by ensembling them, we can always validate correctness of the patch and produce the valid patch as a whole system. So when we designing those agents, we actually selected various architectures and diversify the tool calls and adoption of LLM model at the end. I'd like to highlight a little bit of design decision. Martian follow a deterministic workflow. We have a step for localizations by leveraging all these crazy complex tools like symbolic lookup, stack recovery, and we also annotate the circle with the type system. But we have a very simple workflow in a way that we can work effectively. We also have sub-agent-like systems like Cloud in a way that main agent can invoke, sub-agent can utilize and interact with them effectively. And multi-agent systems also has a group of team and collaborate together to solve the challenges with the same goal of generating patch. If you combine every agent that we have overall against our benchmark, entire of the system can bind the patch against every single benchmark that we design. Our system not just work for synthetic benchmark, we could identify bugs in SQLite and high-profile software in the real. So what's next? We are in the process of standardizing the AIxCC benchmark together with the other teams and DARPA organizers. And we're also in the process of generating common interface for patching in CRS. And we're gonna launch a new project called OSS CRS together with OpenSSF under Linux Foundation. And most importantly, it's time for real world AIxCC. And one of the first attempts that we made as a team Atlanta is that for visual to apply the AIxCC based system in the context of blockchain and smart contract. 4 visible members in our team from Team Atlanta started a new company called QED Auditing with the aim of implementing hyperscale autonomous auditing and pen testing for Web3. If you're interested in, feel free to contact us at the end of the talk. In fact, if you're wondering about our system decision, everything is open source. We have exhaustive document about our design decisions with 100 pages of technical report. And because of AIxCC, we truly believe the world change immediately. And we demonstrate that it's possible to automate the process of patch generations in very fast and scalable and cost-effective manner. Thank you.
Okay, thank you so much, Taesoo, for the great talk. And also, as you mentioned, thank you so much for open sourcing your report. It's more than 100 pages. It's super detailed. Once it open, we read it as well. So thanks for sharing that with the community. Now let's see if I have some questions from the audience. We can take 1 or 2 questions. Probably I will start. As you mentioned in your talk, like I feel like the multi-agent system is very useful, and the workflow now is kind of like deterministic. Do you see a future where we can maybe open another layer of flexibility to the agent, where we can have ultra filtered agent that control all the sub-agent and then automatically decide the workflow by itself? Yeah, do you see a future heading towards that path? Is that necessary, or yeah, what's your opinion there?
So in our patching systems, again, we have 6 different agents.
Right.
One of them has a deterministic workflow. The other agents, like the support sub-agent architecture, and they have a very interesting interaction between main agent, and they divide the tasks in a way that they can launch the sub-agent. But we didn't restrict anything that main agent can invoke. And this is not the future architecture. This is one of the agents that we implement as part of entire umbrella project of Patch CRS.
Gotcha. Yeah, thank you so much. Yeah, we have some quick questions from audience. The first question is, one of the audience is curious about what is the total cost, not just the hardware, but also time of everybody in the team. It's kind of they're asking not only the kind of cost on the money wise, but also the cost on the team member wise.
I think that's a very important question in terms of how to estimate the development cost. to build such a large systems. But I like to emphasize that we are rooted in Georgia Tech, meaning that we are pretty much open team. We actually incorporate many of undergrad, many of master's students, many of PhD who express their interest because it's open community for the purpose of education we adopt. So from the outside, it seems like a very large team. We competed in about 30 to 40 people, but if you count how many people actually work in the full time, I'll say 15 is maximum that you can. If you measure very conservatively, I think we can execute the project with maybe less than 10 people very easily if everyone is actually focusing on. But many people jump in and jump out, and many of the students in our team, we have to educate them during the competition. So I think it's a little tricky to estimate, unlike maybe Theory and Trails of Bit have more dedicated full-time engineers. I think they can describe those aspects better.
Yeah, exactly. It's also the same for us at Shellfish. We're from UCSB. It's kind of exactly the same situation we are facing as well. Yeah, thank you so much. One last question. It's also an important question, like how does the system work for newer or more niche program language, and how does it generalize? Basically, it's about generalizability of a system beyond like what we provide in AIxCC.
So Atlantis multilang actually can support multiple different languages.
Right.
If you remember, the AIxCC actually originally proposed,
Yes.
hey, we have to work on 10 different program languages. That's why we designed multilang at the beginning of the final. So that, hey, we can now really have to prepare to support those languages. In fact, if you have time, there are several requests even internally at Samsung, and they request the support for C#, they request support for Rust. In fact, it's not too difficult to provide or extend our multi-length CRS to support those program languages, but with the caveat. So one of the big assumptions in AIxCC is there is a dependency in harness, meaning that even before initiating an entire project, developers have to express what are the bugs that you care through the harness, the budding driver. But in fact, this is the ongoing work that not just us, that Google also provide automatic fudging harness generation, and we're going to work on automatic fudging harness generations to make this entire adoption of CRS easier at the end.
Okay, gotcha. Yeah, thank you so much, Taesoo, for your talk and for answering all these questions. We will see you again at the panel discussion. Thank you so much. Yeah. Next, we will have Riccardo and Dan from Tree of Beats. They end up with a second place in the AIxCC final, but I remember their CIs was super strong because during the semi-final we have like a lot of badge, like it's real-time badge. 12 Beats get a lot of badge from the semi-final, and then they carry their advantage to the final as well. Without further ado, I give the floor to Riccardo and Dan to introduce their CIs from 12 Beats.
Hey there. So I'll introduce Riccardo and the team a little bit. So one thing that I want to make clear and that I hope people pick up and learn from the Trailbits team is that we had three key principles that we tried to rely on when we built our CRS. The first was that we really prized engineering quality. We tried to build a system that was maintainable after the competition. And in order to do that, we had to build in those architectural decisions, those code quality decisions, that software development lifecycle process early in the development process so that people could use the code that we released afterward. So that shows up in that today we have a robust system that people can download from GitHub that we are continuing to develop and that we believe will be continuing to be useful far into the future. Second thing is that we did not discard industry standard tools. If we had amazing algorithmic tools, we used them. So our system was very deliberate about the way that we used AI. We didn't throw AI at every single problem. Instead, we found good pairings between state-of-the-art tools and LLMs. And I think the last principle is that it sort of relates to the first. We always intended to open source this. There are a lot of people now that are pursuing venture-backed, startups to build things, to productize these sorts of things. But if you're the kind of person that wants a CRS in-house inside your company with full control over the source code and customizations made to it, then the CRS you probably want to use is the one from TrailBits. So with that in mind, I wanted to introduce Riccardo. He's going to talk. He's a core member of the team. And Riccardo, didn't you at some point study with Don? Am I incorrect?
That's correct. Yes.
Yeah.
It's a pleasure to be here with her again.
It's all in the family. Yeah, it's great. Riccardo was a core member of the team and has been with us through this entire journey, and will give you a real technical perspective on the system that we built, the design decisions that we made, and why. So very excited to hear more about our team. So take it away, Riccardo.
Okay. So yeah, I'm Riccardo Schirone, security engineer at TrailBits, and I'm going to talk about our journey to making AIxCC's Buttercup, our CRS, usable to everyone. Before starting though, a short thank you to the whole team behind Buttercup, including Michael Brown, who was the overall team lead and designer of Buttercup, Ian Smith, co-designer, and also huge thanks to the rest of the team who did great work and worked on different parts of the system. So the idea behind the CC is simple. We already talked about that, so I'm going to skip a little bit on this. But Buttercup is the name of the cyber reasoning system that TrailBits developed. And our journey with it began as part of the small business track a couple of years ago. And then in summer 2024, we placed in the top 7 teams during the semifinals. And this summer at DEF CON, DARPA and DARPA-H released the results of the finals event. And there we discovered TrailBits with its Buttercup CRS, placed second and won $3 million. That was already huge success for us. But what our system was able to achieve, I think, is even more interesting for everyone. So we discovered overall 28 vulnerabilities, and we produced 19 patches in the open source projects we were given. And we are talking about projects like curl, mongoose, systemd, and so on. So projects that contains thousands of lines of code, not toy programs. And these vulnerabilities span 20 different CWE categories, like stack-based buffer overflow, out-of-bound read and write, path traversal, and so on. And all of this was done with almost 90% accuracy, which means that whenever our system submitted a vulnerability or a patch, it was actually a real finding or a correct patch most of the time, and not like a false positive. Last but not least, we had a 68 patching success rate, meaning that 2/3 of the vulnerabilities we discovered, we also correctly patched. And as mentioned before, during AIxCC, but also for a real tool, it's very important to fix issues at scale. So let's now look in more detail at Buttercup and see how it works. So although originally it was designed as a much more complicated system, it ended up being quite simple at a high level at least. So the projects or challenges provided as input go through a vulnerability discovery phase that involves a mix of fuzzing and AI to find crashes. And these crashes go to the orchestrator and then our patcher. The patcher's goals is simple. Given a crash, it generates a diff that fixes the crash. And we actually generate a patch only after we see a crash. So we know exactly what we are fixing. We know the input that actually triggers the vulnerability. Both our patcher and our LM-based components for the vulnerability discovery process rely on another component called the program model that analyzes the input challenge and provides tools to extract stuff like function definitions, callers, type uses, and so on. Last, we have the orchestrator that provides proof of vulnerabilities and patches. It interacts with the external environment, like the competition API during AIxCC, and it deals with the duplicating POVs and patches, a very important task. So let's look a little bit more closely at Buttercup's components. First, we can talk about the program model that uses tree-sitter and code query to parse the project's files and retrieve information like function definitions, callers, callees, types. And these properties are used by the patcher and SysGen to navigate the code base. And usually they are provided as tools to an LLM. So by using this static analysis-based approach, we were more confident things would not break. But even if they did, actually, the patcher and CGen had access to other tools, standard LLM tools like cat, grep, and so on, to navigate the code base by themselves and retrieve useful information, even though less efficiently. Then we have our vulnerability discovery component that uses a mix of fuzzing and LLMs to discover crashes. The fuzzer performs traditional coverage-guided fuzzing, and the LLMs are used to expand the fuzzing corpus, and if possible, to find crashes by itself. For the fuzzer part, we relied on libfuzzer and judger, as those were preferred during the competition, but in theory, our architecture could support other kind of fuzzers in parallel. And our CRS spawns several fuzzer bots that periodically run short fuzzing campaigns on a randomly selected harness. So they pick an harness and then start fuzzing that. We also have another service called the merger bot that periodically merges local and remote corpus and keep only inputs that actually improve coverage. And this merging was done to also avoid continuously writing to a remote file system where these corpuses were stored, essentially. Then we have the CGen, which is where we actually use the AI in our vulnerability discovery process. It uses LLMs with some tools from the program model to navigate the code base, and also a few extra tools to execute Python code in a sandbox, try proof of vulnerabilities, and so on. And this subcomponent does primarily 3 different kinds of tasks. So we have an init task, an explore task, and the vulnerability discovery task. The init task is used mainly at the beginning of a challenge to bootstrap the fuzzer with some initial seed inputs so that the fuzzer can correctly exercise the harness code. Then we have an explore task that looks at the coverage data, searching for functions that are only partially covered, and it tries to generate some new seeds that explore the uncovered code. In this way, if the fuzzer gets stuck on some part of the code, we rely on LLMs to unblock the fuzzer, essentially. And finally, with the vulnerability discovery task, we try to generate proof of vulnerabilities from start to finish with LLMs, looking for potentially vulnerable functions, retrieving context around those functions, and then generating crashing inputs. Actually, usually these crashing inputs are generated through a Python program, as also was mentioned in the talk before. So during the finals, we had several instances of this component that would periodically pick one of these 3 tasks randomly and try to produce new inputs for an harness. And if we found something great, we would use the crash. Otherwise, inputs were anyway put in the shared fuzzing corpus so that the fuzzer could explore even further and maybe reach a crash starting from one of the new LLM-generated seeds. The next big component of Buttercup is the patcher that was designed as a multi-agent system, actually at the beginning of the semifinals. And it has a few agents that perform different tasks and they have access to slightly different tools. Given a crash and this stack trace as input, we have a security engineer agent that first understands the root cause of the crash, and it explains it to the next agent, the software engineer agent, that determines the best patching strategy at a high level. And then it tries to implement this strategy by modifying some code snippets from the original code base. The patch that is generated is then built, tested, and validated by a quality engineer agent that ensures the patch can actually be built, it fixes the vulnerability that it was supposed to fix, and that it keeps existing functionalities intact. And if anything goes wrong during this pipeline, we move to a separate step called reflection that analyzes the failure, look at all the previous patch attempts, and determines what to do differently to try and regenerate a valid patch. Finally, we have the orchestrator component that organizes the work of all the other components, and it sends and receives messages on various queues, communicates with the external world to accept new tasks, provide vulnerabilities and patches, but it also deals with vulnerabilities and patch deduplication. So you care about vulnerabilities rather than single crashes, right? Because multiple crashes can, of course, be caused by the same underlying vulnerability. And you also want one patch for each vulnerability, not one patch for each crash. So you want a patch that is generic enough to fix all occurrences of a vulnerability. And this deduplication process starts already in the vulnerability discovery component, which has a very basic filtering step that discards crashes based on a crash token that is embedded in the stack trace. Then the rest of the duplication is done in the orchestrator, which performs some heavier processing to group similar crashes even more. First, based on stack trace similarity, essentially, and then based on the patches we generate. So we group together crashes that are fixed by a single patch so that we can bundle multiple crashes and one patch together. And this was important to avoid sending too many crashes and patches to the competition API. So this is how our Buttercup cyber reasoning system works at a high level. But AIxCC ended this summer, right? So what now? Fortunately, AIxCC was not the end for Buttercup, because at DEF CON, as it was mentioned by Dan, we released a more streamlined version of our Buttercup system that you can find at this URL. And we kept developing on this actually even before DEF CON, because the original Buttercup was developed under a lot of stress, with tight deadline and with some clear constraints due to the competition, of course. But now we can break free of those constraints and try to make this tool more easily available to everyone and expand its scope and functionalities even further. So one of the very first things we did was coding this simple web UI to ensure that you can keep track of what's happening. Before, you had no way of understanding what was going on without querying hidden REST APIs, looking at the logs. But now with this UI, you can easily see what are the current projects the CRS is working on, which POVs it found. You can submit new tasks just by providing the name of an OSS Files project and its Git URL. And you can check POVs that were discovered. You can download them and reproduce them separately if you want. And you can also approve or reject patches that are generated by the systems. I think this feature is very interesting because during the competition, we had the competition API that was kind of validating the patches, and it was telling us if they were okay or not. But in the real world, you might want to review what Buttercup generates and validate it for yourself. So if the patch is accepted, cool. But if it's rejected, we trigger a new patch request within the CRS. And this could potentially be expanded even further with some text form feedback, maybe a natural language explanation of the patch from the CRS as some sort of pull request review process. Another thing we worked on was improving LLM integration. So during the competition, we had a lot of LLM credits. And so having limits or concerns about spend was not a very high priority. But now, however, we do worry more about not spending thousands of dollars while running Buttercup for testing, for example. So you can set up during deployment an LLM budget that can't be surpassed because it's enforced by the light LLM proxy. And moreover, we added support for Gemini, which we didn't have. And we made sure that all components can work with any of the main big LLM providers. And it's enough to have one of the API keys to make the whole system work. For local models, we're not there yet, but it should be easily doable thanks to the fact, again, we use light LLM to interact with the language models. Another key aspect we focused on was local deployment. So Buttercup was originally designed to run on several big Azure virtual machines. For the competition, we deployed something like 70 virtual machines with almost 200 gigs of RAM and 16 CPUs. But yet again, we had a lot of money on Azure credits to spend for the competition, and that doesn't work for people who want to use the system on one project, for example. So since we use Kubernetes to deploy the whole system, we rely on Minikube to easily deploy it locally. And with one command, you can easily do it. Let's say deploying it on a production-ready cluster in Azure is still just one command away. With Kubernetes, you can adjust replicas as needed. Another big usability factor is that you can now run the whole CRS on macOS and ARM, although it was the competition was originally designed for x86, and there were a few blockers to actually enable ARM support, but we did this extra work, and now you can run the system on your MacBook without needing any virtual machine or Docker setup to try it. And we also worked a lot on making the system easily runnable by everyone. So no complicated configuration files to deal with, no secrets or keys to regenerate, to make the various components communicate, tools to pre-install. We made sure to document things clearly, and we created easy-to-use scripts that allows you to deploy and run the whole system with just 2 commands, as you can see in this short video. So you do make setup local if you want a local deployment, or make setup Azure if you want Azure deployment to prepare a few configuration files interactively. And then with make deploy, you deploy and run the whole system. And even though it asks you for a few data and keys, you actually need just one LLM API keys to run everything, at least to start with. Last, we added support for C++ for now, which is very similar to C, of course, but it required decoupling us from what was originally designed for AIxCC. So we had to change our program model component to parse, for example, classes, fields, and methods, and other constructs that are not present in C, deal with the mangling and demangling name. But this is actually just the beginning, as we really want to see this working on new languages like Golang, Rust, Python, and so on. And there's still a lot that can be done on Buttercup, so we are just scratching the surface. And it's really important to make security tools easily accessible and usable to people. So it was part of our journey. There is Kubernetes auto-scaling that can be implemented, extra languages that say more agentic behaviors throughout the system, and so on. So with this long journey, we learned a few things. First, that LLMs are incredibly good at finding vulnerabilities and patching them. And we were a bit skeptical about this task at the beginning, especially for finding vulnerabilities. But with time, we actually changed our mind. We also learned to give LLM well-defined problems, so that by splitting problems properly, you could test components more easily and also achieve better results. And we also try to validate LLM outputs in a deterministic way as much as possible. Even though we did not have a deterministic way to generate the output, we could find some deterministic way to actually validate the output and allow the LLM to iterate on that. So with that, I'm done, and I'll be happy to answer any questions you have.
Cool.
Thank you.
Thank you so much, Riccardo, for the great call. And also thank you, Dan, for the opening remark. We have question for maybe one or two. We have time for maybe one or two questions. Let me start with the most important question from audience, one of the most important one. How can community participate in the development of Buttercup from now on? I saw you have done a lot of effort after AIxCC, but how to bring in the whole community to help with the effort?
Yeah, the project, as we said, is open source. We accept pull requests. There are a few issues that we opened since starting the repository with ideas we would like to work on. So that's a starting point. A few key points I've highlighted in the talk are also some starting point that we would like to see. So we are very open and willing to accept contributions from anywhere. And yeah, I said it's easy to start testing the system even locally and find things to fix. Also, by design, it would be very easy to integrate new components in the whole system and just integrate in the Minikube or Kubernetes setup. I'm not sure if, Dan, you want to add anything on this?
Hey, sorry, I'm double booked, so I had to join a separate meeting. I think the general question was just around community contributions and engagement with Buttercup. Yeah, we have a team of people that are dedicated to continuing to work on it. So we added some basic code quality and testing improvements since the end of the competition. So we are ready to work with people, and a lot of our clients are paying us to build custom additions and enhancements to the code base. Like we invested in building something that was flexible, that had an architecture that was maintainable, that was extendable, and the current system is reaping the benefits of those early decisions. So yeah, please work with us.
Cool. Thank you so much. Maybe another quick technical question. Well, we know like patching is for security, but how did your system ensure all the functionality also preserve when we deploy the generative patches?
Yeah, so I didn't talk about this, but it was in the diagram. But one of the first phase of our patching system was trying to build and run unit tests or tests that were available in the project. So after that initial phase where we could be sure that from the original project we could run tests, then we tested again at the end of the process after we applied the patch if we could still run all the unit tests or tests that were available.
Okay, cool. Thank you so much, Riccardo and Dan, for
Thank
your
you.
time. Yeah. Next, we will have Tyler from the Theory team. They end up with a third place in AIxCC. Very, I personally like their system because it's very AI driven and the code is very clean. Without further ado, Tyler, the floor is yours. Thank you so much for joining us.
All right, great. So I think most people already talked about kind of AIxCC in general, so we get kind of the overview. So I want to talk more about kind of the dream that our team has, right? And I think most vulnerability researchers or security researchers share, right? You have code, you put it into a magical box, and then all the bugs come out, right? And like big code, not just like any code. And so the problem is like, how do we make this magical box in a way that actually works? And this has been kind of the problem for decades, right? We have all of these techniques that people have developed for this, and they all work, right? Like people find bugs every day with fuzzing. They find it every day with abstract interpretation or even grep. But all of these have really shortcomings, right? So some of these are the obvious things, right? We have false positives, sure, false negatives. But there's also kind of these weirder things, right? Like all these techniques require that we are able to build our code, or at least we have all the dependencies. And this doesn't seem like a fundamental limitation until you start dealing with a lot of real world projects, right? You start, things have kind of ridiculous build systems, or maybe you have third-party vendors who don't want to share their code or who are responsible for integrating things. So this actually matters, right? We have big code, right? It turns out that a lot of the techniques that we have maybe start diminishing as soon as our program size starts increasing, right? It works fine on a toy example. When you get to 1 million lines of code, things start falling apart. We also have to deal with modeling, right? So if we're doing something like abstract interpretation or symbolic execution, we can't just say like, here's the code, figure out what it does. We need to lift this into some analysis domain, right? We need to worry about SMT solvers or something like that. And this requires that we have some sort of effort, engineering effort to do this translation, right? This is actually a lot of work. And this is why a lot of these things are very difficult to scale to new languages and so on. And the last thing, which seems really silly, but all these techniques require some really complicated or formal description of what it means to find a bug, right? It could be a simple description, right? Maybe a segmentation fault, some memory access violation is a bug. Very simple description, but that's missing a lot of things in the real world, right? We care about logic bugs. If you're dealing with cyber physical systems, the bugs that we have are much more complicated, right? We don't just care about crashes. We care about things like, did my insulin pump too much insulin, right? And if we want to have an automated system that can find bugs like that, we need to have a formal description so that the code can have some reasonable understanding of what this means. And so the thing is, when we look at how humans do this, it's a little bit different, right? Obviously, this whole graph is a little bit fuzzy with what's red and what's green. Humans have issues too. But if we look at kind of what human do when they analyze code, it's very strange, right? I don't need to build code in order to read it and understand what it does. I can kind of emulate it in my head. If I really want to, I can probably find some tools that I can use to run small slices. I can find bugs that are in deep code, and I can work backwards in order to figure out how to trigger it, right? I'm not limited to shallow code. I can make a lot of assumptions. I don't need formal reasoning to understand that a cookie is tainted, right? I don't need to understand all of the system calls, all of the inter-process communication, and all of the whatever data flow to understand how a cookie got into something, because I understand what an HTTP request is. And humans have reasonable threat models. Humans have reasonable threat models that we've based on kind of real world data, right? I know what insulin pumps are vaguely. So I know that it's bad if they're misbehaving. I know that if I have a self-driving car and it's not stopping, or if the headlights turn off or something, that could be dangerous. And I don't need a formal description to do that. And so this magical box that we have, we'd love it to have the same properties, and it seems like LLMs ought to be able to work in a similar way. So what do we kind of want from this whole system, right? We want it to be cost effective, right? We have humans today, and humans can do security audits, but we need something that's quite a bit cheaper, or else this was a kind of fruitless endeavor. We need to be able to find real bugs. We need to have low false positives. If we're just giving a bunch of junk, then it's going to make people very upset. And at least for the context of AIxCC, we also need to produce triggering inputs and patches. So how do we actually build something like this, right? The obvious thing, right? I'm going to take the Linux source code and I'm going to drag and drop it into ChatGPT and ask it to find bugs. Obviously, this isn't going to work. So fundamentally, it seems like there's nothing really stopping LLMs, right? LLMs have some vague sort of human reasoning ability. That's kind of the whole hope. But practically, we have a lot of issues, right? The first is the obvious one of limited context windows. As we heard about in the first talk, right? Even though some of the context windows may be large, right? They may be labeled as something like 2 million tokens. We have a lot of issues even when we start getting anywhere near that amount. And when we're dealing with large code bases, even 2 million tokens isn't enough to fit the entire code base into the context. We also have hallucinations, right? If we just give our code base to an LLM and ask it for bugs, we're going to get a lot of random junk and false positives out. We have biases and things like that. So the basic takeaway here is like, we can't just magically solve this using LLMs in one shot. But of course, we're not limited to doing this in one shot. So if we kind of think about how humans are solving this problem, humans don't read a bunch of code a single time with a single pass and then output a bunch of bugs. Humans come up with ideas. Maybe they read the code and they sleep on it. They come up with hypotheses and they test them. And so our hope is that we can encode kind of a similar workflow that we use as expert security researchers, and we can encode this into some sort of pipeline or workflow using LLMs. So the first step that we have in our system is basically querying the LLM against every function that we can find. And we give it some sort of pre-built list of bug types that it should be considering. And we output a bunch of data. We prompt it for outputting things about, did you find that bug? But not just that. We say like, are there sources and sinks that are relevant to this bug, right? It's kind of like forcing a certain chain of thought for each bug type to get it to think a little bit more. And the goal here isn't necessarily to solve things in one shot. It's to come up with as many good ideas for bugs as possible. So if we can come up with kind of all of the plausible bugs that exist, we can worry about false positives later. So we can just take a kind of a quick example of what this might look like. The actual prompt is very long. You can see it in our source code. I'll have a link at the end. But whatever, we're going to examine some code. Let's think about sinks for different categories of things, right? So we have some snippet of code here. And the first thing that you realize is this is kind of hard, right? I don't have enough context to do a good job understanding what's going on here. However, there's a few things that I can see right away with intuition, right? This is probably going to do a memory write onto the dest variable, right? I see a source in dest, I can intuit right away what's going on there. So we have something like a memory sink. We also know that cookie is probably attacker controlled, right? Again, I don't need to trace the whole taint through the program to understand what a cookie is. I know that a cookies come from some reasonable attack surface. And so maybe the LLM is going to output something like, great, this looks something like destination might be overflowing in this call. Is that correct or not? Well, obviously, it's very difficult to tell from this limited context. And so we still have kind of the same problem as normal static analysis of a bunch of false positives, right? So our false positive rate is incredibly high at this stage. But we have solved a couple of those problems that we set out to solve. So our bug classes are a lot more flexible here. We're not limited to saying it has to be a memory safety violation. We can say stuff about logic bugs or cryptographic bugs, and the LLM can make its best guess at trying to come up with hypotheses about what constitutes a bug there. The code doesn't actually need to work for any of this, right? I can give it anything that it can read, and it can read through it and try to do a reasonable job. So we have solved some of those big questions that we were trying to. And of course, if we have traditional static analysis, that fits into the same paradigm where it's, bug hypotheses, so we can fit that in the same workflow. So now our problem has shifted, right, from finding bugs to filtering bugs, right? So if we can find a way to remove false positives from a list of hypothetical bugs, then this approach can work really well. So the problem is, how do we do that? And once again, we don't have to do this in a single shot, right? Our goal isn't to take all of these things and instantly accept or reject them. So we can do this iteratively. So just as an example, these are kind of ballpark numbers to make some of the math nice and round, but they're approximately correct. So maybe we run on some code base and we get 10,000 reports, but there's only 10 real exploitable bugs, right? That's a ridiculous false positive rate. But we have a number of different tools. We have classifiers, right? We can ask an LLM to classify each bug as likely false positive or not. This is very cheap because it's a single shot LLM completion, but it's obviously not going to be very accurate, right? So maybe what we do is we set a rejection threshold that gives a 99% false positive rate. So we'll still get 10% of the, maybe take the 10% results. We can run agent triage. Agents are great. They're a little bit more expensive, so we can't necessarily afford to run that on everything. We could also run a full POV generation, which we'll talk about in a second, but that's relatively expensive and takes a long time. But there's not going to be any false positives because if we generate a POV, obviously it's a real bug. So again, rather than doing this in one shot, we can kind of do this iteratively, right? We start by filtering it down with the classifier, then run the simple agent, and then run the POV prediction. And this lets us do something like spend on the order of $1,000 instead of $100,000 if we tried to exploit every single hypothesis that we came up with. So how do we actually do this POV production, right? This is actually a huge problem because the approach that we decided to set out for, we're not doing this fuzzing and symbolic execution stuff necessarily, which would generate these inputs for free, right? The nice thing about fuzzing is if it finds a bug, you have a triggering input automatically. But we didn't do that. So how are we going to trigger these high confidence bugs? So some of the other talks discussed some similar ideas. So the first thing is you don't phrase POV production as an input generation in the sense of generating a string. It's generating a program to generate a string, right? So this is a coding task. There's a lot of nice reasons to phrase things like this. Part of it is that obviously LLMs can't really generate binary output because of how they're tokenized, so that's a huge problem. But they're great at coding, right? That's kind of, Python is kind of like the native language of LLMs. And they have lots of in-distribution training data, right? They've been trained on the internet. The internet has all sorts of POCs for triggering bugs. So this is a really nice way of dealing with that. The next problem that we're going to deal with is that we have to encode our inputs for a fuzzing harness, right? If we're given a program, how are we going to talk to it? And this seems a little bit silly, but when you're asking your LLM to generate code, if your target is something like a web server, it might try to be too smart and just send HTTP requests, right? It may not realize that its goal is to generate binary data. So just as a quick example here, this is a harness from the curl project. And if you look at this, so it's using the libfuzzer format, it kind of takes some opaque data stream and does some type length value thing with it, it's pretty difficult to understand what's going on. So what we do is we feed this to an agent. The agent has the ability not just to read the harness, but to read the surrounding code and come up with a Python kind of library function that can encode the input. So the nice thing here is it can come up with a semantically meaningful input, right? This takes 4 different strings, a URL, a user, a password, and a response, and it deals with all of the actual encoding. It can come up with some docs as well and feed that to the LLM. So the nice thing here is we don't need knowledge of vulnerabilities to build this encoder, right? This can run independently beforehand, and we can test it, right? We can test this independently by making sure that each of those data fields get to where they're supposed to be by using a debugger and saying, if it takes a username and password, did the username and password end up in memory in the variables that I expect them to? The next thing that we're going to run into is just that generating exploits or POVs for things is a really complicated problem. And the amount of data that we have to sift through kind of in this journey to do this is very large. And so we really want to be able to use something to compress our context or kind of keep it clean. So we use sub-agents as much as possible. So in the previous example, right, we can use sub-agents to determine this harness input encoder, and we get a relatively short Python snippet output. And overall, our POV producer, the kind of main agent that drives this process, has no code access, no direct code access. And this is very intentional, right? So code is incredibly long and distracting, right? If we see to-dos in code, obviously that's not exactly malicious prompt injection, but like these sorts of things can be really distracting, and our model has to decide what to attend to. And if we have thousands of lines of code, it's still going to provide some issues. So instead, we can answer questions about code with a dedicated sub-agent that is able to read the code and produce a short output. So the kind of architecture is something like this. So we have our POV agent. These other blue boxes are like sub-agents for these complex queries. So we see the nice thing is these sub-agents have the ability to read code, right? So they have some source reading functions, but these source reading functions are all very grounded. So they can use static analysis and traditional kind of code browsing techniques to do these things deterministically in a very reliable way. If they need to read a definition, they can give the symbol name or something, and we'll do all the work that we can on the back end. We can use grep, we can use gtags, we can use tree sitter or whatever we want to find where that definition is, and then feed it back to the LLM. So that part can run deterministically, and then the overall agent can do a good job. So in addition to those static source questions, we have debugging questions, right? So if it has some sort of script that it's generated that it thinks is a plausible POV, it can run that and debug it. It has access to a debugger and so on inside of that sub-agent. And then finally, we actually have to test the POV. Obviously, the agent can run this on demand if we want. But we also run it deterministically, right? If this POV ever succeeds, we can terminate instantly. And if the POV agent ever decides that it thinks that it has succeeded, we can run this test POV and make sure that it didn't lie and hallucinate. So, the agents are really nice. I think everyone who is here in attendance understands that agents are wonderful, but I do want to drive a couple points home. So obviously, agents are a lot more expensive, right? Your context length is going to grow quadratically because you have to keep going back and forth, repeating all of the previous messages that you had. So your costs run up over time quite significantly. But the context that you're able to get makes hallucinations and reliability much better, right? So it's a very powerful technique. But developing a lot of the tools around this, I think, is still a very nascent thing that we don't have good answers for. So the tools need to be simple. You need to include all the tools. But we've done a lot of research in like human usability studies and ergonomics, and we don't have a lot of the same things for LLMs. I think one of the big things about this in particular is that you really should not include extra tools. People think that tools are kind of like some option that you present, but if you think about it, these are specifically added to the prompt. And if you think about how this works, like I like to think about it kind of like a video game. Like if you're playing a video game, and someone gives you a portal gun, you know what to do with a portal gun, right? You shoot portals at things and you jump through them. And if you're playing this game and someone gives you little jumpy stilt things, you understand that this means that you can jump to high places and you can fall from heights and you're going to be okay. So these tools, in a sense, are guiding how you're going to solve the problem. And if someone gives you lockpicks and you're playing the game of Portal, it's actually going to really confuse you, right? You're going to, every time you get stuck on a puzzle, you're going to say, wait, is this where I'm supposed to use lockpicks? You're going to go try and do these things, and it's going to get really confused. So you need to be really careful with that. So, that's all kind of abstract, so we can talk about this real quickly. There's a lot of text on the screen. We're not going to go through it all. Basically, we can run some system message, give our agent some information about the project that it's going to run. We can give it information about the harnesses and a bug that we're trying to exploit. It has access to tools, right? It can run these sub-agents. It can ask for more details about the bug it's trying to exploit. It can use a sub-agent to figure out which harness it's going to pick. Again, this is a nice example of compression where this is a relatively complex query. The amount of context required and source that it would need to read to figure out the answer to this question is quite large, but the overall answer is going to be quite short. Eventually, it starts generating some POV code, runs it through some debugger. The debugger is going to answer a natural language, telling it about kind of what's going on, blah, blah, blah. We get the idea. So this can run for a while. That example ran for about 40 minutes, and we can see the output. So it's able to crash the specific assigned integer overflow vulnerability that it was prompted with at the beginning. And the input for this is actually pretty non-trivial. So this is the full input, including the comments that the LLM generated for the POV. And here's kind of a hex encoding of it. So this is a pretty interesting vulnerability, especially because this is actually a 0-day and free RDP. So this wasn't something that was injected and meant to be found. This was kind of a real vulnerability, not found by fuzzing. Free RDP is found, it's a OSS fuzz project. So there's a lot of things that this technique can do that kind of go beyond what's possible with fuzzing. So patching, I don't want to spend a lot of time on patching. I think there's a lot of interesting things here, but today people get the idea about what coding agents can do. I think this was a lot more exciting 2 years ago when we started, but at least, we get the idea. So overall, did we meet our goals? I think we did, right? This is relatively cost effective. Generating these POCs is something that we can do for a few dollars, which is kind of incredible. We can find real bugs, including 0 days. We found a lot of 0 days, exploitable 0 days in name brand software, let's say. Low false positive rate. We were able to produce triggering inputs and patches. In terms of us at Theory, we've done a lot of things post AIxCC. So we have support for other languages, JavaScript, Python, Solidity. We can also run on binaries. So we can do kind of a similar technique running on assembly code. We have CI/CD integration. We actually run our CRS on our CRS commits now, which is kind of fun. So anyway, just to wrap up, I think LLMs can help work on this kind of human static analysis problem. You don't need to solve these tasks in one shot, right? Trying to figure out a workflow, separating kind of hypothesis generation and testing is a very general technique. We can design our agents to make things kind of more efficient and overcome a lot of these shortcomings. I also want to emphasize that this is one approach, and LLMs are kind of a really new and awesome technique that apply to a lot of different areas. So I think there's a lot of new ideas that still need to be explored. So our source code is also open source. I've got some kind of QR code here, got some blog post information, source code. If you want to browse those agent trajectories and read the whole thing, they're all there. But yeah, thank you.
Cool. Thank you so much, Taylor, for the great talk. Sorry, we are a little bit behind of time, so probably just directly start the panel session, and then we can ask you a question during the panel session as well. So it's the same. Yeah, maybe let's start. Taesoo, Riccardo, and Dan. I will start with the first question. Since we are discussing AIxCC, I have seen a lot of new technology being developed during the competition through the 3 amazing CIs. For each of you, could you please maybe summarize a little bit the key strengths or innovation in your solution? Maybe you can start from Taylor since you just finished.
Sure. Yeah, I think for us, we have done a lot of things around fuzzing and kind of these traditional techniques. It's not something that we are not familiar with, but I think that our whole hope and hopefully what we've proven is that it is possible to use LLMs to mimic this human workflow and do a lot of this stuff kind of directly in a way that there was really no tools for previously. So I think there's still a lot of work there, but I think that's a big innovation and a big exciting area.
Right. Just a quick follow-up before we go to other solutions. You mentioned like we want to LLM to like simulate a human workflow. I totally agree that should be like our end goal. And then you build all those sort of like agents with sub-agents. What's the kind of high-level like mindset do you have when you build the topology of these agents, right? Like I remember having like hundreds of sub-agents working together parallel. So what's the principle there?
I think a lot of it is trying to think of basically how, again, if I was a human working on this, every time I'd kind of like do some sort of context switch or try to answer a question anything that's a simple question that has a simple response is probably something that could be an agent, right? And again, both for context compression purposes, because a simple response means we get to compress a bunch of context into a small answer. But also just for kind of this division of labor purposes that seems like a reasonable trade-off. I think there's a lot of questions still about like, you do want to share some information about memory, things like that. So it's not entirely clear, but yeah.
Okay, cool. Thank you so much, Taylor. Maybe Taesoo, you can answer the question as well.
So I really like many of the decisions that Theory made for the competition. And we also had tons of interesting research ideas that we wanted to execute because it's a competition. And we also wanted to win. So we actually made lots of practical decisions behind the scene. I think one of the most important criteria for us is how to maintain fault tolerance. I think, in fact, it turns out that's the most significant, most important aspect of the competition schedule. Your system should function for, say, 4 to 5 days without any interruptions. You should be able to analyze random repository. And there are tons of surprising things happen during the competition. It turns out our system also suffered from many of the issues. We couldn't even build many of the projects. We skipped the entire project, for instance. But at the end, some components arrive during the competition and start progressing. I think that's actually very important for the competition, probably very important for the real life as well. When we're designing some autonomous systems in the future by using AI, but I think more practical way, I really like how Theory organized everything, and also like what Buttercup design and semi automated way. This is what we actually did for internal deployment at Samsung as well. We also have web user interface. We don't need tight integration between bug finding and patching. And patching is not always correct. So we give you more chance for developer to iterate over their automatic generated patch before generating PR to the GitHub. I think these are interesting directions, but I really like the force tolerance aspect of our CRS design for the competition.
Cool. Thank you so much, Taesoo. Anything you want to share, Riccardo?
Yeah, I think one of our key strengths was finding a good balance between traditional solutions and LLMs. We used LLMs where we thought they were good at, and traditional solutions for problems they were good at. So we leveraged the strengths of each world. And yeah, we focused first on a robust and stable system that could work reliably. So I think that paid off for us.
Cool. The next question we receive, since this is AIxCC, we talk about AI. From your experience, how much does each step of your CIs benefit from AI assistant? Which step you say the AI jump in and help the most? Which step you say AI is not playing that important role? Maybe we can still like go back to original other stuff from Taesoo and then Trailbase and then Theory.
I think many of the CRS in the final design of our Atlantis heavily rely on AI, I would say LLM. Previously, most of the program analysis, it seems like, again, as Taylor mentioned, is great in terms of their idea, and in theory, they should work. But in reality, for one of the good examples is symbolic executions. We had a huge problem of just enabling symbolic executions in any of those open source projects. It's too big. And instrumentation and during the compilation process, it breaks something very unexpectedly in every single project. So how to deal with those? And LLM, as the theory mentions, like has a fundamental benefit of resilience because they just process the text-based reasoning, and then they can do some actions at the end. I think this is a remarkable benefit. So if you think about what are the things traditional software analysis you can replace with LLM, that's a very interesting idea. Your idea is widely open. One of the key idea, one of the interesting idea we discussed heavily in our team is how to replace concurrent executor with LLM. In fact, in theory, there's some places like checking the correctness of comparison by using hashing function. It never be able to proceed if you have a concurrent execution behind the scene. But LLM can recognize, hey, this is a hashing function. It's not core features of the program. Hey, just replace the hashing function with identity. In fact, this is amazing decisions. To oversimplify the input, not relevant to the original constraint to the input space. In fact, there's a potential that LLM can significantly improve the possibility of analyzing large real-world software outside.
Thank you. Riccardo, anything from, yeah.
Yeah, for us, I think for the patching side, AI, of course, has helped tremendously. Like before, there might have been tools to patch autonomously a subset of use after free or a single class of vulnerabilities, but now like the problem is much more easily solvable. For our vulnerability discovery step, instead of say, AI could improve a lot on that part for us. And yeah, applying approaches like what Theory and Team Atlanta did, more agentic behaviors on the vulnerability discovery side. Instead, like for us, it was more of a using LLMs to help the fuzzer. We could rely more on like the LLMs to do the actual work. So, and like it could improve even more our system, I guess. So there's space to improve there.
I think yeah, like to Riccardo's point, patching, like I guess if you think about all this, Taesoo Kim mentioned the Cyber Grand Challenge, right? That was 10 years ago. And in some sense, all of these things like automatic bug finding is possible, right? We had that before LLMs. There were no GPUs in the Cyber Grand Challenge. But some of the things that changed, right, is being able to run on source code and like produce patches that humans can look at and be happy with. It's kind of incredible. And even the traditional, we have program synthesis techniques and things like that from academia, but those don't work anywhere near the same, and no one would like those as patches. So I think that was a huge thing that everyone immediately made use of. I think for us also the POV generation, right? Finding bugs you can still do with static analysis, traditional techniques, but the actual converting of this seems like it could be a bug into here's an input that triggers it. There's not really another alternative aside from fuzzing or something like that, but for targeting a specific bug, you basically need LLMs or something like it.
Okay, yeah, thank you so much. I feel that makes sense because LLM are generative models. So in terms of generating new code, like POA is also part of generative tasks. I'm good at it, which make perfect sense. Probably like talk other side of the story is that we know like during the process, we use LLM extensively, so do have experience also regarding the good and the bad. Let's talk about the bad side. Like from each of you, what do you say the key limitation of current LLM in terms of finishing all these tasks? Right, so maybe we start from here. Yeah, Taesoo, what do you say the key limitation of LLM in your experience of
I
team
think
time?
one of the things that the
Mhm.
organizer or AICC in general didn't highlight enough is that there's a huge chance that LLM already observed all the open source projects that we analyzed during the competition. I think this is weird, but you can think the amount of budget in the organizer side that they cannot create the ridiculous big project for the competitions, right? This is a little bit weird. But at the same time, because LLM already trained on top of those commits, so they're leveraging some of the recall or some of the memory residue inside the weights when generating patch and stuff, probably work out pretty well. But in terms of real world code repository, for example, some internal code bases is Samsung, and none of the LLM actually observed. I think we see some huge performance gap between, particularly when we are handling large source code repository. I think we need some form of online adaptations if there is a chance to do the very short fine tuning on the code bases so that we can respect some of the coding conventions inside. And similar to human learning about the code base, we need some, before doing anything, probably LLM should do some adaptations and generate some rags and index and whatnot, so that capture some of the big idea before doing any security task. I think there's a little bit of gap between what we demonstrate in AICC and when we are actually handling larger scale source code that they never saw before.
Yeah, exactly. Data contamination is one of the pain for us as well. Like sometimes you feed model with the function, the model automatically tells you what are related functions because the model has been trained on it. But yeah, as you mentioned, if this internal code base model cannot do this and then there's not enough context, model may make mistake for sure. Yeah, so like Riccardo, what about like your experience? What's the key kind of pitfalls of LM?
Yeah, I agree with Tiso, Kim, on the aspect of handling non-open source projects. Like this was also one of my faults. Because, yeah, would the AICC work that well if it was on big closed source projects? It would be nice to see. But yeah, that's an important aspect. And in terms of limitations, I think there is one aspect I would like to highlight, which is the indeterminism of LLM models. Because like you could try the same prompts, the same inputs several times, and maybe one time out of 10, it will give you the right answer. It will think about the code in a slightly different way that will unblock a whole different path. And this indeterminate is kind of, we could say a limitation, but it's also slightly different from other security tools we have, because with other tools, you get, like, you have the same input, you get mostly the same output usually, but with LLMs, there is this indeterminism that make applying LLMs for security tools a bit harder. Like with agents and iteration loops and so on, you can reduce this, but yeah, it's still kind of a problem, or yeah, a slight limitation, I'd say.
Yeah, I think just kind of in a similar vein to what Riccardo is saying, there's evaluations of these systems is really obnoxious, right? So especially when you have an agentic system, one of the really cool things is that your agent might run a tool and the tool totally fails, and the agent handles that robustly, right? It tries it again with different arguments, or it switches tools to something else. But if you're trying to build this system, it's very obnoxious if you introduce a bug and the system just kind of, it's okay, I won't worry about the bug, I'm going to keep going. And it doesn't fail, but now it takes twice as much money to run or something like that. And so every time you want to do these evaluations, like if you have to run everything end to end, it's super expensive. It's just, we don't I think that kind of as software engineers or researchers, we haven't really figured out how to really work with these tools in the most efficient ways. And I think that's kind of the main limitation in my mind.
Interesting. So we talk about randomness, talk about like stability of the two AI themselves, talk about data combination. But what do you say the limitation of the capability? For example, is there any limitation we have seen for like certain type of bugs, the model just cannot analyze it? Right, from like capability perspective, what do you see the limitation?
I don't know who that's directed at. I guess since I went most recently.
Yeah, maybe you can just.
So I think, there's some things where there's definitely a lot of biases in how the models are trained, right? So even like when we switch from one provider to another, we'll see things like maybe they're very safety tuned and they really hate saying that, oh no, that's a false positive, because false positive means that you're making a very strong assertion that something is safe. So there's a lot of these biases around kind of that sort of thing that I think are quite difficult. But I think fundamentally my belief is that, if we stop doing like LLM, like frontier models today, I think there's still a lot of like probably at least 2 years of research that could keep coming out of using the exact same models with the capabilities we have today. It's like, I really think that obviously there are limitations, but the limitations are really on how we interact with the models, and it's better models are better, but I think it's kind of a human tool interaction problem as opposed to a model problem.
Sure. Anything you want to share, Taesoo or Riccardo?
So when we are writing software in general, after several interactions with the software and their design, we can think of next step. Hey, this is a way to improve, and this is the work that we have to for the next round of iteration of our systems. When we are writing agent, we realize even after we're completing this, we don't know what to do. Tinkering around the prompt, tinkering around some of the architecture, hope that it works out. This is a little bit annoying as a program. And then my workflow these days is that I'm really particular about certain implementations. Now, instead of solving it, I try to ask agents all the time, which feel like I'm dumb anymore. and at the end, I start analyzing their output and try to comprehend their logic behind, which is almost impossible. And this is a similar problem in improving model capability. Probably after they train on certain data, other than increasing the amount of data, like what are the next, if you truly understand the model architecture, you should be able to say that this is a way to improve, right? But we don't know what's the next thing to do. In fact, no one in the world can propose other than keep trying and hope that it works out. In fact, this actually reflects how we did in our development, in our agent side. We don't know what's the best model. Hey, try to just put all the complex tools. Hey, it seems like it's directed too much. Hey, let's just simplify the tools. Hey, we talk too much in the prompt. When you're using reasoning model, don't say anything. Like all these random brute forcing in human developer side is super annoying, and probably the fundamental, like it actually took out most of the joy of development when we are building some of the agent for CRS in our team.
Okay, thank you, Taesoo. Riccardo, what do you think?
Yeah, I agree with them. But also, I think one of the main limitations is what you have, I think, in the training set, like working on some topics that were not well covered in the training set can make, of course, the LLM work harder. But also it depends on how you interact with them, as Tyler said. Like maybe you can work around some of those problems they have with some specific language, or maybe working with binary data that seems to be harder for the models to reason about. Maybe you can transform the original problem you have into something that the LLM can understand. Like as we say, most of us has generated Python code to generate the input. We didn't ask the LLM to generate the input, and that's kind of one of the limitations. But we worked around that with some extra tooling. So I think there are of course limitations, some languages or topics that LLMs might not cover well, but we can find ways probably to deal with them.
So I have
Go.
another point that I like to highlight is that the feeling that I have when you're dealing with this LLM, my software is not future-proof, meaning that we believe there's a new capable model, like say GPT-5, which actually appear immediately after the competitions. Most of the software actually adopt to the latest model, like latest improvement in the other side. But what we experience is the opposite. Although it improves certain area, but there are larger pros and cons, and certain workflows work better and the other work not. And the software that we're building probably become obsolete if, say, AGI exists in the future, or drastically improve prompt. Why do we need agents? We just solve everything, right? So many of the things that we are working on right now is all about how to address incapability of existing LLM. And by creating some structure in a way we can tackle very small problems that we really care. But said that, today's LLM is capable enough that we can utilize them in right way and useful way that we never thought of possible. But most of the work that we're doing will be very quickly obsolete if we have much capable model in the future.
Yeah, this is exactly the good point. We have seen during our competition experience as well, model gets updated and a lot of things we build is longer useful. Since we talk about this, we have like two other philosophy level questions we want to ask before ending this panel discussion. First is that what do you think AI will beat human or surpass human capability in terms of cybersecurity tasks? Do you think that is possible? If yes, do you have kind of like inversion of the possible timeline?
If you're asking me, probably surpass is a little bit overall the term. For example, in speed. In fact, one of the I don't recall one of the team actually participated in the live CTF in the final last time. Before human understanding anything, the agent actually discovered the flag and got the flag and submitted the score. So in terms of speed, for low-hanging fruit, LLM actually does pretty good job. But convoluted task or some complex tasks might be faster in terms of end-to-end manner. But one of the things that we can apply those LLM-based techniques, anything they can horizontally scale. For example, given a lot of number of embedded devices and websites, applying those agents in horizontal scale, you can easily beat. And this is not a future AI, the current AI already beat in the scale because we have limited time and limited resources. But if you talk about the complex, say, can you find the zero-day vulnerability? Can you do better than most capable human outside? Probably still take time, but the people who have access to those LLM might be able to leverage even quicker and much better than AI alone, for sure.
Yeah, Riccardo, what do you think?
Yeah, I think AI has kind of become already in some aspects a sort of replacement for human. We have seen it like with the Expo. They can do some, they can find some very nice vulnerabilities in some specific topics, but in the general sense, I'd say it's more of a tool, and I hope it will remain a sort of a tool for experts to use. So of course they will make us faster, and maybe we will shift like our focus on some more novel tasks and leave these easier tasks to an automation tool, AI or not. But yeah, I hope in the future we will just shift focus to more novel and complicated tasks more and more. And it's just gonna remain a tool.
Cool.
Yeah, I mean, I think I have kind of the same opinion, right? It's like if you asked, when are fuzzers going to surpass humans? Like in terms of total number of bugs found, I imagine fuzzers have long surpassed how many bugs humans have written or vulnerabilities from POCs people have written. But that's not how it works, right? Like a human uses the fuzzer as a tool. We have like this for a long time when people were talking about kind of AI, kind of the last time people were talking about AI, we had kind of all this discussion about like centaur chess, right? You have these automated chess engines, but you pair them with a human, and it turns out, at least for kind of like 2 decades, that was still beating state-of-the-art chess engines. Now I think it's no longer the case, where the human's just not useful. So I don't know how long it's going to take before the human has no place. I think there's still a lot of very novel things that humans come up with, right? Like CPU level attacks, or like kind of weird logic bugs that I think are very difficult for computers to reason about. So I think that sort of thing is going to remain in our domain for probably several years. But as Taesoo said, like there's totally places today where obviously these systems are faster, they can scale better. So in some sense, they're beating certain aspects of humans already.
So I think I also have some anecdotal examples. We discussed those subjects a lot in our lab with our PhD student. After participating in AIxCC, as a hacker, we've been exposed to AI, and they realized, hey, in fact, we can be replaced. So instead of being replaced in the future, hey, let's be part of the other side. So let's replace together. That's why they're creating PhD program. All of them now start a company because they don't want to be replaced. So they are the capable hackers and programmers, and they felt threatened in some sense. So it's good time to be in the other side, finding a way to replace the human hackers, at least expand the capability of auditing to the older people, which previously only limited to the resource-heavy company, for example.
Cool. Thank you so much. We have one last question, but since we go over time a little bit, let's try to keep the answer short. But we do want to get your opinion on that. It's very important. It's follow-up of the current question, like who do you think will benefit more from AI at this stage? Attacker or defender, either in the short term and in the long term? Yeah, maybe
So
you can say.
if I start, I think Defender has more capability of utilizing their hidden proprietary information than Attacker. So I think I like to see more efforts like XBAL in more white box testings in the developer side, rather than pure black box testings in offensive side. Because Defender, as a developer of the software, they can decide how much information they can share together with LLM. I think short term and longer term is always have better capability in terms of protecting one single software, targeted software that you care about security. Because attacker side, again, similar to horizontal scale, you can tackle one of the components. But I think as a defender side, it's a good tool to leverage before exposing most important asset, your source code, to the attacker side.
Gotcha. Thank you so much.
I actually think that in the short term, attackers might have an edge, as AI is just yet another tool in their arsenal that they can use to find one single hole in a system, and they need actually just that. So they don't need to secure a whole project. They just need to find one vulnerability, one crash, and they're good to go. But in the longer term, I think defenders will actually benefit more from AI as they integrate AI more in the development, CI/CD. Think about like applying Buttercup or similar CRS in production during development. So it's gonna become more integrated with the development, and it's gonna benefit the defenders, I think.
I think I'm on the optimistic side. So I think right now, attackers already have the capability of developing exploits. Like that's not a novel capability for them, although maybe their efficiency increases. But I think the defenders right now have very limited ability to find these vulnerabilities, maybe because that's not their skill set, or maybe because they're busy with other things like patching. So I think adding the capability of vulnerability discovery to defenders, I think that's going to benefit them significantly. So I think that this is a defense favoring capability overall.
Hey, thank you so much, everyone. Thank you, Taesoo, Riccardo, Dan, and Taylor for the great talk and for the great panel discussion. We learned a lot from this session. Thank you so much again, and congratulations for your great achievement in AIxCC competition. It's super amazing.
Thank you so much for having us.
Thank you.
Yeah. Thank
you
you
for having us.
Thank you. So from now on, we will start with session 2. The session 2 will consist of 3 talks from Frontier AI Labs, the OpenAI and Anthropic and Meta. And our first speaker is Newton Cheng, and he's the cyber lead in the Frontier Red team at Anthropic. And Newton, please take it away.
All right, thank you so much. Let me go ahead and share my presentation really quick. Here we go. Hi, everybody. Like Eugen mentioned, my name is Newton Cheng. I currently lead the cyber portfolio of a very interesting team here at Anthropic called the Frontier Red Team. My talk is, the goal of my talk today is to just talk a little bit about kind of how we at Anthropic are sort of viewing the really the problem of cyber offense being accelerated by AI, increasingly powerful AI models, and kind of what we think we should be doing about it. So just as a little bit of an introduction to what my team does overall, we are called the Frontier Red Team because in some sense what we're trying to do is we are trying to figure out what the worst case scenario for cyber misuse of increasingly powerful models looks like. We do this by trying to measure capabilities based on our experiments. We try to predict when models will have certain levels of capabilities. And what we ultimately hope to do is we hope to demonstrate these capabilities that we are saying we should be concerned about in a safe and controlled setting. And what my team does is we specifically consider the concerns around cyber misuse. And so some other words that some folks in the audience might associate with this type of work is dangerous capabilities and risk, kind of everything under this umbrella. I don't usually like to stick to these phrases too much because I think they're just really broad, and I'd like to be a little more specific about what we actually mean by this. Now, traditionally, what we've done is we've tried to talk about threat models, and this is a slide taken from a talk I did at DEF CON CTF and the AIxCC hub earlier, or so not DEF CON CTF, at the DEF CON conference earlier this year, and the question always comes back to like threat models and trying to be like really specific about, oh, here is like the risk profile that we're concerned about. Here are the threat actors we're concerned about. Here are the types of capabilities that matter. I think many people, both on this call and in the audience, probably already have a pretty decent idea. So I don't plan to go really in depth here. What I will mention is, I think, at a very high level, we sort of think about 3 types of actors when we're thinking about cyber misuse. We think about, on the left here, we think about, AI as a tool that can upskill relatively low-skilled actors into looking like higher skill actors. We think about threat models that look like, at least in terms of impact, significantly increasing the scale of relatively low-level attacks. For example, you could imagine like massively increasing the scale of relatively simple ransomware or phishing type attacks, things that from a technical perspective maybe aren't so impressive, but AI kind of enables someone to do this at much larger scale. And then there's a threat model, I think, that is more unique to AI models. The first 2 threat models, I think, are sort of very commonly attributed to even standard every pen testing tool that's ever come out in the security space. And I think something that is in some sense quite unique to increasingly powerful AI models is a threat model that looks like elite actors able to become significantly more efficient and productive through through the use of AI models such that they can essentially parallelize or scale out their workflows, so that instead of just one APT group or one actor performing a single operation, they're able to parallelize and increase their workflows to like 4, 5, 6, 7 APT level or elite operations. And again, I won't go into too much detail about like the specifics of these, but at a high level, these are kind of like the 3 types of risk actors that we're thinking about. Now, I think a traditional story for the way that the community and we thought about this problem even just a year ago was we thought, okay, what we need to do is we need to get better evals in place. We need to make sure that we have all these things like methodology and mapping evals to types of capabilities kind of on point. And to be clear, this is still really, really important. I think, however, that one of the changes that as a frontier lab we've gone through in the last 12 months is we've kind of moved on in terms of how we think about and how we're using evals internally. Certainly, they're still useful for things like tracking capability progression, but we've sort of progressed internally, at least, into treating evals almost as just milestones for capabilities that we expect to reach. I have here like a Slack post from one of my team members from our recent 4.5 release, where kind of in some sense the absolute value of evaluations is somewhat less important to us than just like models being able to do things that we thought they couldn't do before. And the way that I've been phrasing this in the last few months has been, I think, our thinking around evaluations, at least within our lab, is that we are trying to move as much as we can from models doing proxy tasks that we think map to capabilities that we care about, to just trying to get models to do the actual real thing that we care about when we talk about, model risks or risks of cyber misuse. And so, for example, one of the kind of classic scenarios that we think about in terms of cyber misuse is, people will try to use AI models to attack enterprise networks, or they'll try to compromise networks of industries that are important to the economy, to the infrastructure. And to that I say, great, rather than us trying to piece together proxy tasks of evaluations, sort of some types of capture the flag competition, capture the flag challenges, something that map to very specific parts of what that process might look like. My team is very much in favor of, okay, well, we should just try to build as close as possible a facsimile of what compromising one of these networks looks like, and then throw our model at it and see what happens. See if it can do it. If it can't do it, where is it failing? And for an example of what this actually looks like in the real world, I put this link here of our wonderful safeguards team who have been working like crazy for the last year. A couple months ago, they released this really great threat intel report where they put out some of the most interesting case studies from the last several months about actual real-world usage of adversaries trying to leverage our models to do cyber misuse. And there's some really, really nice examples here, including, for example, a probable Chinese APT trying to compromise Vietnamese infrastructure and telecommunications. There is a nice story of how we disrupted a North Korean fraudulent remote employment operation that was trying to leverage our models for that, which is all just to say, following up from the previous series of talks, we're already pretty deeply in the regime of people in the real world, of adversaries in the real world, already leveraging our models to try to undertake real cyber operations. And I think that, especially within the frontier labs, we're not really in a position where we have the luxury of just looking at these types of proxy tasks that aren't necessarily fully representative of what is actually going on in the world right now. We tried to do this sort of earlier this year in a collaboration we had with Carnegie Mellon, where we demonstrated that Claude back then, I think that was Sonnet 3 or 3.5, we demonstrated that it was able to replicate the Equifax operation from several years ago. And that, I think, really kind of started our push internally, or certainly my team's push, to say, okay, it was able to replicate things that were able to happen in the past, and now combined with the types of real world examples we're starting to see in these threat intelligence reports, okay, like we are firmly past the point where models probably can't do things that are actually useful for even, I think, APT level actors out in the real world. And I think ultimately the most concerning thing about where this leaves the state of cyber offense, this leaves the state of cyber offense augmented by AI, is you could imagine a world where you have a model that is not just replicating Equifax once, but is, you can spin up like your 100 different agents as long as you can, pay for the API costs, and you could be running like 100 Equifax operations all at the same time, and for relatively cheap. And so this is sort of like the state that we find ourselves in the near future of, okay, this is what AI augmented cyber offense might look like. And so going back to my slide about, okay, here are these like 3 threat models we're thinking about, I think the picture that you want to have in mind is, okay, this isn't just a case of, like a standard in the same way that maybe a traditional pen testing or red team tool might have, where it sort of makes a particular or single workflow easier to work with. We want to be envisioning a world where, okay, when we're talking about AI assisting adversaries, we're talking about AI models that are increasingly powerful, that are increasingly autonomous, that can, we think, like very soon reach the point of being able to do near autonomous end-to-end cyber operations. And that, I think, is like really the sort of concerning place that we need to be building to, or we need to have in mind as we're kind of figuring out what should we do about securing our own systems as well as possible. And so maybe, unsurprisingly, and based on the title of the talks following mine, I think that the conclusion that a lot of the frontier labs have come to certainly is, okay, well, the way we combat this is we need to be trying to leverage our AI models for cyber defense as much as possible. And so what my team is thinking about, what we as an organization at Anthropic are thinking about, is we're thinking about it first, I think, from the perspective of, all right, well, we know that models are able to, maybe with some assistance and increasingly less assistance in the future, start to do cyber operations. We know we have real world examples of elite level actors trying to deploy AI models to perform their operations. Okay, well, if we can use those same capabilities, we can use those to find gaps in our own security posture. We can use those to find the places that our systems are insufficiently defended against, and then significantly accelerate our workflows for actually securing those systems. I think this is like a philosophy that is probably pretty commonly held by most people in the audience from the security industry. This is, in some sense, the classic, yes, offensive security is a key and integral part of actual good security posture. I think really, in some sense, the only message I have from that perspective is, okay, well, you really have to mean it when you're trying to use these models to red team your own systems. You really are trying to emulate as much as possible what actual adversaries are doing. And for that, I mean, I think there's really a non-trivial amount of work that goes into taking a model and figuring out, okay, how can we elicit the maximum amount of capability from these models? In some sense, that's like the core mandate of my team under the Frontier Red team. We try to maximally elicit models to figure out what they can do. But that's all just to say, I think that as we are doing evaluations, as you are running these types of simulations with the models, it's really important to try to give models as much as you can to make them as good as possible. And this means giving them the full suite of tools, for example, that actual security researchers or actual red team pen testers would actually be using. That it's not good enough to run evaluations that look like, here is just my base model that doesn't have any tools except maybe a basic like Bash or Python tool. You really got to give it like the full suite of things, because certainly the adversaries out there who are trying to use your models to do bad, they are not going to only give the model the minimum number of tools possible. So that, I think, is really like the first level of what a good cyber defense looks like and how we can leverage our models for cyber defense. I think the next level is to say, okay, well, suppose we have a good handle on the offensive security side of things, which, to be clear, we don't necessarily have. But what we should then try to do is we should also try to deploy our models or use our models to do active defense that looks like, hey, models, find vulnerabilities in our code so we never even ship like buggy code that is vulnerable. Hey, let's use our models to try to help secure the open source community and try to minimize the risk of, for example, like supply chain attacks on some of the most widely used open source software and packages on GitHub. Hey, let's do things like just do responsible disclosure of CVEs in these things so that we can mitigate or we can shrink the total surface that attackers have of actually deploying models for cyber offense. So I think a really key part of what it looks like for us to successfully employ AI models for defensive purposes is exactly, hey, let's use models to actually secure our code. Let's use models to secure our systems in an active way. And then the next level after that, which I saw my colleague Joshua Saxe might later be talking about from his perspective, is we can even go one level further and try to then deploy autonomous agents for cyber defense that are actively securing your systems, actively hardening your systems and code bases beyond just what you might be doing at the developer level. And I think ultimately, this is really the posture that we really need to get to, where we are using our models to massively accelerate and scale out both our offensive and defensive security posture, because this is essentially, in my opinion, the only way to meaningfully defend against the wave of AI augmented cyber offense that, again, we're already seeing. And so it's not really a question in my mind of what should we be doing, but these are all things that we need to be doing. And I think if you only take away a couple messages from this talk, I would say, one, models are getting a lot better. For people who might have looked at the blog post we released alongside Sonnet 4.5, you might have seen we had these evaluation results about model capabilities. And I want to emphasize that it's not the absolute value of evaluation performance that we care about, but rather the main thing to take away from our results is, hey, the gap between the lowest, this gray line and the top level orange line is 7 months. And we're obviously only going to be going up from there. And so, the main takeaway, I think, from my presentation is models are getting increasingly powerful. People are already using this to try to do bad things and try to do cyber offense. We need to be right now building our systems with that expectation in mind. We need to be arming defenders as much as possible so that they have a chance at keeping up with the massive scale of AI cyber offense that we might expect to see in the very near future. And that's all I got. Thank you so much.
Thank you. Thank you for the great talk. So we can have some Q&A session, and we got like some questions from audience. And the audience said that the categorization of threat actors for threat modeling AI is interesting. Is it based upon some assumption or threat intelligence on IOC, TTP as of the threat actor?
Yeah, so this is definitely an ongoing discussion. I think that this certainly my description was pretty high level. It's partly informed by sort of historical ideas around threat modeling in the cyberspace before AI became a big thing. In some sense, a lot of AI tooling follows a similar path to other like red team or pen testing tools in the space. But certainly, I think, and especially in the last 18 months, increasingly informed by our internal threat intelligence efforts, by what our safeguards team is actually seeing people are using the models out in the wild. And like I said, I think we've already seen examples of essentially all three of these classes of actors, and we're continuing to improve our ability to catch and disrupt these operations.
Thank you so much. Because the time is up, and we will cover more questions in panel session. So yeah, see you again soon.
All right.
And
thank you so much.
Yeah, thank you so much. And the second speaker is Ian Berlinsky, and he's the research program manager at OpenAI. And yeah, thank you, Ian. Yeah, please take it away.
Hello. Hello, everybody. Let me see whether I can get the slides up as well. Are they actually presenting? Can you see anything?
Yeah, I can see your slide.
Okay. All right. So I'm the research program manager for cybersecurity research and products here at OpenAI. And I'm going to echo some of the same themes that Newton brought up, but also from a different perspective as well. So the main topic that I'll be chatting about is how we advance AI's defensive cybersecurity capabilities and how the community writ large can get involved in getting that done and moving the ball forward with making AI better advantage defenders. And I'm going to get there by a kind of roundabout way, starting with talking about the Zoom tab isn't working. There we go. Starting with an announcement of our recent product from my team called Aardvark. Some of you might have heard of Aardvark. If you've been involved in AIxCC or you're part of any of the security blogs or Twitter threads, etc., you've probably seen news about OpenAI's Aardvark. Basically, at a very high level, what Aardvark is a code security agent that connects to your Git repo right now, builds a threat model of what your code does and all the surfaces, etc., and then scans it and finds vulnerabilities in those commits, validates those vulnerabilities in a sandbox, and issues patches through our product codex, and then pushes that forward for human review. I don't bring this up to convince people to necessarily sign up to beta test Aardvark, though it is open, but rather to highlight just how much models have advanced over the last couple of years. We started a few years ago with a lot of the AIxCC work, focusing on whether or not people could even do something like this, whether people could advantage defenders over attackers by leveraging AI. So there's been a lot of work across different dimensions like code security, network security, privacy, etc., in looking at how far we could move the ball forward with advantaging defensive uses of AI. And the goal of this obviously is that AI is a helpful agent that augments human beings and makes defenders' jobs easier while making attackers' jobs more difficult. There's obviously a balance to that we all recognize, and that Newton, you spoke to from Anthropic's perspective. But we definitely believe that AI will advantage both sets, attackers and defenders. And our goal is to make sure that we advantage defenders more. And so in order to do that, this is a community effort, and we need the help of everybody to move this forward. So starting a few years ago, DARPA had the AICC challenge, and I saw in the previous session there were some competitors from the AICC challenge there. And it really opened the door to autonomous agents that advantage defenders with code security. And I've been involved in this from only about a year and a half, 2 years ago when I started at OpenAI, but it's been incredible how far the technology has come just in that time. And you can boil it down on why the technology has advanced as much as it has. And you can say that it's because people have been spending more time on it. You can say that teams have built better systems or whatever. But underpinning all of that is that the models keep getting better. And you can offload more work to the models that previously you had to orchestrate around. So about a year and a half ago, and these are evaluations, by the way, for cybersecurity that were performed for our preparedness framework. About a year and a half ago, the best models we had were kind of getting some questions right in some high school level challenges. They weren't really doing that great on professional level things. And most of the models required a lot of hand-holding to get them to do what we wanted them to do. With the introduction of reasoning and tool use, the models have become so much more powerful at tackling harder and more complex problems. And it's not a linear scale of it does these things just simply better. It's that it's unlocking whole new skill categories within the model of how to tackle these problems, how to think about these problems, how to orchestrate across much more complex sets of data and get to the answer that we're looking for. And I think this line is going to continue going up. I don't know whether our current benchmarks are going to be able to capture the nature of this line, because we're already approaching, and this data is probably about 6 months old, but we're already approaching the limit to the benchmarks that we've got. And so that begs the question: how do we really push this tech forward and make it something that superpowers or supercharges the humans involved in defensive AI? And that brings up the question of what matters in training, what matters in evaluation of these models. And right now, some of the evals could definitely be better. So what worked probably about 6 months to a year, 2 years ago, isn't necessarily challenging for the models anymore. And so simple evals where we're getting a correct answer out aren't quite as powerful as evaluations that are more representative of the entire environment, have more complexity, have the skills that we need to elicit out of the model actually tagged and understood, and we have more clear understanding of what skills need to build on each other in order to get to the point that you can tackle something hard. And thinking about it from the perspective of actually training like a person or an entity how to think about these problems requires that same sort of pedagogical breakdown in the skills required to solve these things. So having evals that are representative of those skill sets, that break things down and are able to show when the models are just lucky versus when the models are actually hill climbing being good, is useful for a range of different things. It's useful for actually getting the models to be smarter at this, but it's also useful at highlighting when a model might possess the skills to do something concerning, and when we might need to add additional mitigations to models because of that. So having that resolution of skill composition is critical. And in terms of the environments, having runnable, realistic environments that have that are representative of the complexity of the real world is important. Being able to run these and reset them and be in that same environment again without the environment changing and without adding ambiguity to the training environment there is important. So having complex environments with the ability to reset them and having easy access into them so that the models can participate in them. Having a good grading criteria, figuring out how you would grade whether or not a model's doing well at a task is important. Tool orchestration. We're finding that, like I said earlier, reasoning and tool use are some of the most important things moving defensive cybersecurity forward. And we're working really heavily on the reasoning side for cybersecurity, but the tool orchestration and tool use is something that the community can help with as well. Building AI capable and native tools that our models can use easily, having documentation that the models can learn from, and effectively making it possible for the models to use the tools out there to streamline their own work and turbocharge their own efforts so that they can turbocharge defenders' efforts as well. And then finally, contamination and reproducibility. Contamination is a really big thing. If you publish an eval set online and it's scraped and incorporated into training data, it's no longer as powerful as if it's held out and kept back. So having the ability to create training environments that are potentially unique each time or have variability potentially mitigates that. Also holding out eval sets also helps that cause. So kind of wrapping up briefly, and I'm mindful of the time as well. Why are we doing all this? We're doing this because the world is slightly scary in some regards with respect to software security, with cybersecurity. There's been, what, 40,000 CVEs reported this last year, and that number is growing. We need to mitigate software security. And if we can mitigate software security, if we can mitigate network security, if we can understand how to handle data more privately, et cetera, and use LLMs to turbocharge those efforts, everybody's safer. You don't have people falling for scams necessarily, or having their computers hacked, or getting a letter in the mail saying that all their data has been stolen because we had a data breach. This stuff matters, and it's not just for the people involved in cybersecurity. It's not just for people that know how to code and are working on digital products. It literally affects every single person on this planet right now. And if we want to make life better for a lot of people, making robust, secure systems and potentially using AI to do it is a strong way to get that done. And so we hope that the community will figure out a way how to work together to build better evals, to better understand the capabilities of models, to help us with realistic problem sets and environments, et cetera, because that's how we move the ball forward in advancing this cause. So I'll wrap it up there, mindful of time.
Thank you so much, Ian. We have some questions. The first question is, as you mentioned, AI capabilities are really rapidly increasing. And given this, evaluation is really important to evaluate the AI model's capability more accurately. And then because the workshop is about cybersecurity, and so I have a question, do you have some thoughts on what kind of cybersecurity benchmarks are urgently needed the most? For example, you mentioned some issues of the current benchmark, such as contamination and reproducibility, the issues. But beyond that, what kind of cybersecurity benchmark, including task, are urgently needed? You have a thought about that?
Yeah, so our team is focused with the announcement of Aardvark. This is kind of evident as well, but our team is focused largely on code security to start with. The the focus areas in cybersecurity are broad, and you can also focus on network security. You can focus on scam detection. You can focus on privacy. You can focus on literally any of these areas. We felt that code security was the largest bang for the buck for initial research, but all of these areas are critical. And if somebody wants to make a huge contribution, tackling one of them that the models don't really do that great of a job at right now is a way to do that. But doing that in a way that follows a lot of the guidance that I just said earlier, meaning it's an environment that can easily be stood up, that's reproducible, that has an easy entry point for the model to use, and has a grader attached to it on the inside, preferably a Dockerized container. Making it easy to plug and play these evals in is the easiest way how to get them used and how to make sure that they're incorporated into model benchmarking and potentially training as well.
Okay, sounds good. Yeah, so because the time is almost like off, so given this, we can move on to the last the speaker. The last speaker is the Joshua Saxe. He's the AI security tech lead at Meta. And Joshua, take it away, please.
Thanks. Here, one second. Let me share my slides.
Sure.
Hi. Okay, I'm Josh, and I work on AI security at Meta. And my talk today is about the roadmap to achieving AI security automation for defenders. So I have like a lot of slides here, so I'm going to talk very fast, but hopefully I'll be intelligible. So first, I want to define my terms a little bit. So by cyber autonomy, I'm talking about a broad set of capabilities that spans a very large and diverse sort of technical tent. So here's a tree map of the size of the varying sort of sub-markets within the cybersecurity market, just as a way of sort of thinking about the scope that we'll need to automate as we look to automate cybersecurity with AI. So it's not just finding bugs and it's not just finding and fixing bugs in code, right? It's also monitoring all the network traffic that edge devices and enterprises experience. It's also cloud. It's also identifying like access management issues and compromise in cloud deployments. It's also endpoint security, etc. So there's a whole lot of different types of. Sorry, let me mute my work messages. Okay, there we go. Yeah, there's a really diverse set of services sort of under this tent, and all of them, I think, should be seen as in scope for automation. And by AI, I just want to ground this. I really mean machine learning models that basically can do what you train them to do. So I'm talking about LLMs here. Can generalize to some other things that you didn't train them to do. But then if you didn't train them to do certain things, like, for example, agentically browse your cloud access permissions and identify issues and autonomously fix them, my expectation and my prior is that you can't expect the LLMs to actually accomplish those things. And so, okay, with those two definitions in hand, I think that we're not as far along as some of my colleagues think towards true cyber autonomy across all of those different areas. But I do think that there are a set of technologies that can allow us to make like really dramatic progress over the next few years, and I think most of all, agentic coding sort of paves the way. So here's a slide from, I think I'm not picking on OpenAI here, but I think it's a good example, like the OpenAI GPT-5 system card showing progress at an AI agent agentically hacking a set of cyber ranges. And you can see that we haven't made a huge amount of progress in getting LLMs to do this. And then here's the famous meter plot where we see that there's an exponential increase in the ability of LLMs to at least half the time solve coding challenges of progressive complexity, and that's sort of going up exponentially. And I don't think, so there's been a ton of progress in areas that we've focused on, like coding, and less progress in areas where I think justly the big AI labs have not focused on building sort of agentic capabilities. But I think that the set of technical tools that are being used to hill climb agentic coding capabilities, so pre-training, supervised tuning, where we use expert data to train the models to behave agentically, thanks to expert contractors who are producing that data, and then reinforcement learning within software engineering environments. I think that sort of recipe at a high level, I think is going to be very useful for automating cyber, and I think the defenders are going to need to do that first. Yeah, so I think adversaries are going to start building these capabilities, and I think defenders have to do that too. I think that we really need to set our sights in the defender community beyond co-pilots and aim at true autonomy. So it's not enough just to find some potential bugs in code. We also have to prove them out, like the previous presentations demonstrated, and then eventually actually fix them. It's not enough just to find some hypothetical access management issues and in an enterprise's access management deployment, we need enough confidence that we can actually entrust that kind of agency to an AI over a human. I think we have a long road to get there, but I think that needs to be the goal. I think what we need to aim for is more like Waymo in the path that autonomous vehicles have traveled, and less like Clippy, like an assistant that sort of sits alongside you and serves as a kind of convenience feature, or maybe increases your productivity by 5 or 10%. So we need to set our sights much higher than that. Okay, so I just wanted to give some theses about how we work towards meaningful autonomy. So first, I think we need to take the possibility that we could, achieve meaningful levels of autonomy seriously over the next few years, and that our adversaries could too. So we need to work with a sense of urgency. Like I said before, I think that there are disciplines within AI that have made much more progress towards autonomy, and so I think we need to take inspiration and guidance from those disciplines. For example, like coding and research agents. I also think that we need to start taking evals much more seriously in security. So we don't have sort of like ImageNet quality evals across the whole range of security disciplines that I showed on the first slide. And I think that's a blocker and a friction point to realizing our autonomy goals. I don't think, and I'm going to argue this in more depth later, but I don't think prompting general purpose LLMs is going to get us there. I think it'll get us there in terms of assistance and some level of some sort of progress around some autonomy verticals, but I don't think that it's going to get us all the way there. And so I think we're going to need to look at actually fine-tuning LLMs for the security verticals. And then I think we're going to need to rethink cybersecurity ultimately is a very process-oriented discipline that involves lots of stakeholders coordinating and working together. Those processes were invented for the pre-AI era, and I think we're going to need to rethink the way in which we structure teams and the way in which we actually perform cybersecurity as organizations responsible for defending people's privacy and security. I think this is a harder problem than other areas of machine learning. Enterprises, so AI, the lifeblood of AI is data, and enterprises keep their data private. Lifeblood of AI is data, and attackers obviously keep their data private. I think the big AI labs are incentivized, and this is not a critique, it's just sort of the game theory and the economics of the situation, to dominate the larger markets, like general chatbot use cases and coding use cases. And so there's just less funding for security, and these are all challenges also to realizing these capabilities. I'm going to skip over this slide, but I'll go into some ways that I think we can address these challenges. Okay, so now I want to give the kind of maturity model that we're using at Meta around thinking about how to begin to solve for autonomy. Lots of folks at Meta are building AI agents, as at many of your organizations as well, for cybersecurity. And usually the way this process starts is we start experimenting with general purpose LLMs to see if they can solve a given security problem. And we don't really have evals, or if we do have evals, it's like a handful of examples, and we get the agent working sort of based on vibes. This is sort of the crawl state. I would say most agents for security are sort of in this state of maturity right now. The inevitable problem here, and I think that even in academic literature, we are still often in this place, although thanks to work like the work at Don Song's lab, for example, on like evals like Cybench and CyberGem, I think we're making a tiny bit of progress. The current state often, though, is like there are lots of different evals. None of them are good enough to be canonical. And so you get lots of different papers published, and they're based on different evals, and the results are incommensurate. What we need is something much more like ImageNet, which allowed the computer vision community to sort of hill climb, like one sort of eval operating system and compare results across papers. And we don't have that for like the vast majority of cyber disciplines. And within organizations, you know, we often don't have evals. Like within big companies like Meta and Google and this kind of thing, they're also we haven't solved that problem also. Okay, so oftentimes I think folks in the cyber community are attracted to sort of like doing this like fun kind of stuff, like building complicated multi-agent frameworks that coordinate a bunch of different LLMs and use, you know, like novel MCP tools and RAG and this kind of thing. Actually, oftentimes it's much higher leverage to do the sort of boring work of building like very good evals, which then allow AI approaches to be compared and allow teams to actually hill climb results and get better and better results. Okay, so that's the sort of crawl state. In the crawl state, we don't really have good evals, and the sort of exit criteria for the crawl state are to build them so that we actually have like an empirical hill to climb. In the walk state, at least the way we're thinking about it at Meta, we still aren't fine-tuning LLMs, but we have really good evals, and we like really good offline evals, you know, so that we can gauge how good our systems are, and we're sort of beginning to build online evals. And so what this gets us is the ability to say, change your system prompts and then actually know if that improved your system or not, right? I think this is like a huge, this is a simple thing, but it's like, this is a huge problem across AI security is many of us are in the state where we can't change a prompt and really know with confidence and in a way that's uncontroversial, like within our team or our community, whether that was good or bad, right? And so in this walk state, we've sort of finally solved that problem. Now, like the inevitable problem with, I think, being in this walk state, if you're using sort of generic general purpose LLMs, is that you are just hoping that the general purpose LLMs that you're using were trained on data that will generalize to your problem. And anybody who's actually tried to get LLMs to produce like security business value within large organizations, like probably knows that like the amount of futzing you have to do with an LLM to sort of like understand your organization's private data or legacy code or private documents if you're doing stuff like detecting data exfiltration. That's a frustrating place to be. And so ultimately you do need to, I think in many cases, not all cases, but in many cases you need to fine tune LLMs on your own data. And that's because LLMs still have this property, right? They're still machine learning models. They still do really well on in distribution data. They do an amazing job of generalizing out of distribution, but that's limited, right? And then there's a universe of things that LLMs cannot do yet. Okay, and then the final sort of most mature stage that we're sort of using to define our maturity model at Meta is this run state where we're really in the kind of operating model where we have offline evals that we trust that allow us to hill climb efficacy. We have online evals that allow us to monitor performance in production on like the actual production distribution. We can do A/B testing. We also have training data, and we're, at least in many cases, we're fine-tuning our models, and we're in a kind of mature, like we're in a mature state in this run state. And I think it's really urgent that across security we get to this run state for the reasons that Ian and Newton mentioned before. We don't have the luxury of like sort of slowly and incrementally like realizing autonomous defensive security. We are racing against adversaries who we should expect are developing their own autonomous capabilities. So we need to figure out how, like, and this is a hard problem because security is such a complicated discipline. I mean, there's like such a big technical difference between detecting data exfiltration versus, you know, doing tool calls into fuzzers and like formal methods tools to analyze code. But we have to solve all of those problems in order to compete with our adversaries. Okay, I want to talk a little bit about data foundations now. So like, it's interesting to me that that there's a huge surge of interest and also progress in getting LLMs to find, improve, and fix bugs in code. And I think the reason why we're seeing that is that the big labs have invested very heavily in getting very high quality data for agentic coding. Not so much agentic code security, but agentic coding. And the investment's been pretty remarkable, right? So here's like an estimate of how much the various labs have invested. So, you know, in this estimate, this is all based on public data, so there's like a wide confidence interval here, but Google has invested like $100 million in paying contractors to create custom supervised fine-tuning coding data, and other labs have invested tens of millions of dollars as well. I think we're going to need to do the same. So we're going to need to find ways of doing this in cybersecurity also. Like, I don't think we're going to get. So I think all of this investment has helped with AI security, like code security capabilities. I'm not sure it's going to help us solve like cloud access management, for example, or malware detection, or detecting living off the land attacks when an attacker is sort of midway through their kill chain. I think we're going to need separate data to solve those problems. And we can't rely on sort of the downstream effects of these coding investments there. I think we're going to need to build lots, and we're going to need to figure out how to build lots and lots of RL environments for LLMs. The big labs have been investing for the last 18 to 24 months, I'd say, in building very good and diverse coding environments. But we're going to need to do the same thing for areas of cyber that are sort of outside of the code security domain. I think CyberGem is a great example. I mean, this is in the code security space, but I think it's a great example of like an early entry in this process. But we're going to need like 100x more across like many different cyber disciplines. And there's just like a vast difference between doing like the RL step in LLM post training against a given vertical and not. So I mean, here's just a screenshot from the R1 paper earlier this year where they show they went from 20% AI ME accuracy to like 85% after doing RL training. I think we're going to see similar dramatic step functions in cyber autonomy, but we need to build the environments to actually do it. And I think this is the way we sort of get out of just like futzing with prompts and hoping the general purpose models sort of solve our problems for us. Because I think the general purpose models will solve some of our problems, but many of them we're going to have to solve ourselves within the AI security community. Okay, so I only have a few more minutes, so I'm going to go really fast through the last few slides. So I also think I think that transforming cybersecurity with AI is as much an organizational sociology problem as it is a technical problem. So it's a kind of socio-technical problem where we need to rethink the processes that we use. So for example, think of like a security operations center as a sort of bundle of human processes coupled with like technological tools that mediate those processes, and then like an org chart and a whole bunch of practices that sort of maintain that org at steady state in terms of hiring and the kind of people that we hire. All of that, I think, is going to need to transform thanks to AI. I think we need to be thinking about those more sort of organizational sociology transformations like in tandem with the technology changes that we're going to need to implement. Yeah, so it'll take just as much experimentation, and I don't think we can design this whole thing waterfall style top down. I think we're going to need to, all the folks here working in cybersecurity and AI security, I think we're going to need to experiment here and sort of share learnings as a community and sort of learn how to structure those sort of AI security organizations of the future. Yeah, so I think the roles are going to change, the org charts are going to change, and the processes are going to change. So okay, wrapping up. So I think that I think that we are on a path towards achieving significant autonomy in AI security, but I think our agency is going to play a critical role in actually getting a good outcome. So I think we can expect that attackers are going to use the technical tools that are now in the public domain around how to train LLMs to solve like specialized agentic problems. So for example, attacking a network and sort of walking a kill chain. I think that as defenders, we're going to have to move faster than them in order to make sure that there's a good outcome in AI security. There's a huge opportunity here. This is the most exciting time in my like 20-year-long career in cybersecurity. So looking forward to see what we can do together. And I'll stop there.
Thank you so much, Joshua. We have some questions. And first, you actually claimed we need significant autonomy and labor productivity gains as fast as possible. Otherwise, the adversary wins. So would you mean that significant autonomy and labor productivity gains will not benefit the adversary significantly? Or can you explain more like how you think the significant autonomy and labor productivity gains like benefit more the defenders than attackers?
Yeah. So I'm not sure I totally understood the question, but like if I understand correctly, I'm not taking a position on who's going to benefit more from AI. I guess insofar as I'm taking a position, I'm just saying that I think that attackers and defenders both have the tools. I think basically like the current training, the high level training recipe that we have for LLMs, where we do pre-training and then like to roughly speaking, we do pre-training and then we do sort of supervised fine tuning and then we do reinforcement learning. I think at this point we have good evidence that can be used to achieve significant intelligence and autonomy. But I don't think we're going to get that for free in cybersecurity. I think we're going to have to build it by building our own RL environments, building our own like high quality supervised fine tuning data sets. And I think like basically the race is on to see who does that faster. Bad actors or good actors. There's just I don't know what the outcome's going to be, but I know there's urgency for defenders to build sort of our side of that.
Got it. Understood. Yeah, I agree. And another question is, okay, so you mentioned that the many companies are now investing in coding related data, like to get like a better like model. And do you think there is a way to reduce the cost of generating good coding related data? Like for example, we can use LLM or other AI models.
Yeah. So the question is like, how can we get good? So is the idea? So I think the question is how do we get cheap, like
reducing the cost,
like security data, like for
Yeah.
Yeah. I mean, I think that some of it's just going to be expensive, but so I think that the labs and also cybersecurity companies are going to need to pay the cost of getting like high quality data from cyber experts, just in the same way we paid for. I mean, folks here probably know, right? There's a whole industry around producing high quality expert data in many different domains, and I think in domains where there's the most of it, which like I think coding is a great example. We've seen huge progress. So I think we just are going to need to pay the cost in cyber, and so that's a problem for the big companies and venture-backed firms and stuff to sort of, and also grant funding agencies and this kind of thing, to figure out. I think like one an optimistic thing I'll say is that reinforcement learning is like dramatically more data efficient than supervised fine tuning. So if we can figure out ways, I don't think this applies to every cyber problem, but I think it does to some. I think we can figure out ways to build RL environments that model real world problems in a good enough way. That's great because people have probably seen the papers showing how data efficient RL is. It's like orders more data efficient than SFT. So I think there's some hope there, and sort of identifying problems that can be RL models through environments that we build.
Yes, sounds good. Yeah, it's really useful. And last question is actually it's the same question that I asked the Ian. Do you have some thoughts like on what kind of cybersecurity benchmarks or tasks are urgently needed the most currently?
Yeah, good question. I think these are very hard to. I think where the most value is, or like the sort of some obvious things, but I think will be uncontroversial here. And so investigating alerts. So like an enormous amount of human labor goes into the manual process of like seeing a security alert and then investigating to see if it's a true positive. I think, and there are many big companies and also AI security startups and larger AI security companies who are trying to build alert investigation automation workflows. But I think we're in that kind of crawl state where if somebody comes to me and says, "Oh, I have this alert investigation system, it works great," it's just like, trust me, bro. Like, that's the level of evidence that they're providing, and there's no evals that actually can give a kind of a leaderboard over who's doing best. So I think that's a big priority. But I don't know how to solve that problem given how much private data is involved. I've got some ideas, but if anybody can solve that problem, I think that would be of enormous value to both the academic and industry community. And then I think the work that folks here are doing on like CyberGym and that kind of thing, I think that's like super valuable also. Because even though I think bug finding and fixing is the most mature area of AI security right now. I still actually think we've got some distance to travel before we have like an ImageNet quality canonical, sort of set of evals. So and that's useful too. Anyways, those are just some thoughts.
Yeah, I agree, because like many current cybersecurity benchmark focus on like different tasks. So yeah, actually to address this issue, we also like built some observatory where we collect all existing like cybersecurity benchmark, and then by doing so, communities can monitor like different aspects of cybersecurity capability in AI model. So yeah, okay, sounds good. Yeah, thanks for the great talk, Joshua. And yeah, from now on, we will start the panel discussion among Ian and Newton and Joshua. And actually, before starting with this panel discussion, yeah, let me just tell the announcement to audience. We are now collecting some responses for our like survey to see to like collect the people's opinion on the balance between cyber offense and cyber defense. And we posted this survey link in the YouTube, the chat. So yeah, audience, please feel free to take the survey. After the workshop. And from now on, let's just start our the panel discussion. So first, like each of you are from the frontier labs. So I expect that you have like different experience or different lessons for each of you, the company. And our first question is, have you ever observed an increase in attempt to misuse your models for cyber attacks or malicious purposes? And if so, then what kind of misuse activities did you observe the most? And yeah, maybe we can start with Newton.
Yeah. So I think that's maybe one of the running themes across really all three of our talks is that we've seen, I think, an increase like across the industry as a whole, as just more and more threat actors are experimenting with these models kind of across the board. It's not limited to any not necessarily limited to any specific labs models. It is in the attacker's interests really to just like try to expand their portfolio of tools as much as possible. And I think like what we, like I was saying in my talk, I think what we know to be true is that attackers are getting increasingly sophisticated with their model usage, that they're experimenting with, like Joshua was saying, that like in some sense they are already in the process of optimizing how to better use models at greater scale. And so I think it's really sort of like what we're seeing is just across the board, across the entire industry of AI labs, that like increasingly complex scaled misuse of models is going to be a major problem moving forward.
Yeah, so you also like observe like increasing activity of misuse for spam or phishing, like because I also like encountered like Anthropic recent the blog to this like about the recent misuse activity of a cloud model. So like you encounter like some increasing activity of spam or like some phishing using cloud or something like that.
Yeah, so I think like we so our safeguard team, like I was saying, I think they sort of try to regularly publish these like threat intel reports of what we view as sort of like particularly interesting cases that we've caught and disrupted. I think like a really a key part of that is exactly that, ultimately for better or for worse, I think my colleagues at the other labs probably feel the same, that like safeguards and this whole like sort of trust and safety teams are really going to be a super key part for better or for worse in the next couple of years of really like improving our ability to catch and disrupt these types of operations. Yeah.
Okay. How about Ian? So have you ever observed like in increase in misuse?
Oh, of course. As AI proliferates and people become more aware of all of its different capabilities, and as it becomes better, people are going to start using it for malicious purposes. So internally, we've got several different teams focused on everything from threat actors targeting our systems, and we stop that. and also threat actors using our systems for abuse externally and against other people. The latter, we've reported several cases where, for instance, nation states have used our models to create obfuscated code snippets, to string together multiple different things to create tools and whatnot for their uses. And we've announced and published some of these things, but yeah, nation states and less sophisticated attackers are going to use AI as much as they possibly can, and it's going to be a cat and mouse game. And whether we're able to effectively catch all of them we'll see.
Sounds good. How about Joshua?
Yeah, I probably can't. I'm not cleared to say anything that we haven't published publicly, so I'll just speak in general terms. Yeah, we've observed some of what my colleagues just described. I mean, a lot of our models, as everybody knows here, a lot of our models are open source, and we've also observed that attackers, like there's some cases where attackers have fine-tuned them, to use them maliciously. We've also observed like Cisco has now a line of models based on Llama 3 that are like fine-tuned. I forget what I think on like 500 million, that kind of order of magnitude, like security specialized tokens, which seem really promising from our perspective also. Yeah, I think this is going to be I think like I don't know, I'd be curious to hear what other folks on the call think, but I feel like this is like, like the first days of COVID or something, and it's like we can't index too much, on like the stories that we have now around attacker use, like because like probably there'll be like a number of qualitative notches that we're going to hit around attacker autonomy here, and we're in like the very beginning. Like that's where my impression is like the practice of offensive cybersecurity and the practice of defense of cybersecurity have been changed a bit, but haven't been like qualitatively like revolutionized yet. So I'm like more thinking about like the next few years than like what we're observing right now.
Yeah, we agree. We all like. I think I believe that all of us are seeing more and more news about attackers misusing AI. Okay, thanks for the answers. And the second question is, how do your internal red teams or adversarial evaluation processes in each company test your models for potential cybersecurity misuse vectors? And can we start with the Newton?
Yeah, happy to. So I think I sort of alluded to this a little bit in my talk. I think we certainly, I think, have in some sense our classic, like we have our suite of evaluations that we run related to various cyber capabilities for people who are familiar with our responsible scaling policy for a long time. We've sort of had these commitments around particular evals that we run, and we're developed for that. We do pre-deployment testing with external partners, and kind of very recent and sort of more recently, in some sense, the mandate of my team was, okay, let's also try to, as much as possible, build out systems that are like as close as possible to the actual mock-ups of like the types of misuse that we're seeing, sort of trying to move away from proxy tasks and more to the real thing. And so for, again, very similar evaluation challenges that my colleagues at the other labs discussed, but I think really the big one is we're working hard to develop increasingly sort of facsimiles of the real world misuse that we're concerned about.
I'm just curious, actually, like cybersecurity attacks are really broad, and there can be more new emerging activities over time. And how can we ensure that we actually tested like all of the possible activities?
Yeah, I think this is like an eternal problem in security of how do you make sure you cover your entire risk surface, including the ones that you don't know about. I think a lot of it is just, obviously spending a lot of resources in terms of being diligent across the entire stack of system security. Like my colleagues were saying, it's not just finding all the vulnerabilities in your code. It's making sure that as a whole, your entire system has a good security posture. And it's about really leveraging as much as possible, like the amount of data that we're getting right now about like the TTPs and the signals in the real world of what people are actually using the models for.
Thank you. How about Ian?
Sure. So capabilities are super important, right?
Yes.
Like if something is incapable of doing something, then monitoring it for use in those cases is not as relevant necessarily. So that goes back to the evals discussion as well. We have a preparedness team at OpenAI that if folks look up OpenAI preparedness, you'll find all of our recent documentation on this. And one of the topics we track is cybersecurity and the ability of the models to be used for various actions within the cybersecurity domain. And this is an evolving conversation. And I'm definitely not going to speak to all the details and where we're at right now with all the nuanced thinking underneath it. But looking at evals as a way to understand what skills could be strung together to do various actions with the models is, in my opinion, probably the best way that we can think about this in this group right now. So that again is a call for better evals, more realistic evals, really understanding skills underpinning those evals and benchmarking based on that.
Sounds good. How about you, Sean?
Yeah. So we've been like pretty public about our cyber testing. So we've got like 4 papers. Like the first 3 are like CyberSec eval 1, 2, and 3, and then we've got one called Cyber SOC eval, which is like a defender capability eval. Yeah. I mean, so I think I think we all read each other's system cards, right? I think our strategy's pretty similar to OpenAI and Anthropic. We're interested in. I think we've all. So I would love to hear my colleagues speak up if they see things differently. But I think we've all sort of converged on a point of view where we're not just like a couple of years ago we were focused on detecting like predicting attacker uplift, and now we're interested in predicting both attacker and defender uplift when we release models, and looking at a more holistic picture where we consider sort of in-lab attacker uplift estimates, in-lab defender uplift estimates. But then also sort of intersect that with our understanding of the threat landscape, so we actually understand how a new model might what marginal benefits that'll provide to attackers and defenders in the actual ecosystem as it stands and where it's going. Yeah, that's the way we're thinking about it right now.
Yeah. Actually, one interesting thought I have in mind just during this conversation is we might just make some optical AI, like the fine-tune to be a bunch of cybersecurity data, and then we can see like what the optical AI are doing, misusing our like different, like some AI system. By doing so, we might like explore what kind of cybersecurity the misuse can emerge or something like that. It was just one of my thoughts. Okay. Okay, another question is, another question is, where do you see the most promising applications of AI in enhancing the cyber defense? Can we start with Newton?
Yeah, this is something I feel I'm pretty enthusiastic about. Joshua was alluding to, I think the strategy that we have at Anthropic is, we are trying to prepare for this world of really like how AI augmented cyber offense, and we think that the best way to fight this is we really want to arm defenders and make defenders as capable as possible, because that's how we see doing it, and that's not just. Certainly there's many things that are very what I call like developer coded, like, we find bugs in our code, we fix them, we patch them. This is all great. But again, as my colleagues were alluding to, cybersecurity is way more than this. Even just like SOC tasks of triaging security alerts and doing threat investigation and doing threat intelligence properly and well. All of this is stuff that is really integral to actual good security posture. And so I think initially right now where we're at is we are doing things like vulnerability discovery and patching because that's related to code. And I think that a key part of leveling up our applications is, one, pursuing this more autonomous defensive agents, and 2, figuring out how we can deploy AI across the security stack to handle things like SOC, to handle sort of things that maybe are less flashy than just like finding 0 days.
Yeah, thanks for the response. And how about Ian?
Yeah, building on what Newton said, the challenge isn't necessarily starting to get people using the tech. People are already using the tech for the entire stack of defensive cybersecurity capabilities.
Yes.
The challenge that I see right now is that the models are capable of so much more than what people are actually deploying for. And finding ways, and this is across the board, it's not just a cybersecurity problem. This is even in writing and planning and reasoning, all that stuff.
Yes.
So finding ways of getting those applications to the end users in a way that doesn't require far more sophisticated understanding of the cybersecurity domain that they're operating in than that user has is important. So how do you get these defensive capabilities to a small company that maybe doesn't have the expertise in cyber but needs to defend themselves, make their code base more secure, works, defend their users, etc. And so that, I think, is the gap right now, is getting the applications of the models in cyber to be more easily integrated into workflows and out there. So I think there's some catching up to do with that, while at the same time improving model capabilities overall for these domains.
Okay, sounds good. Yeah, thanks for the response. How about you, Sean?
Yeah, I guess I'd just add, like, I'm assuming that like there's there are a lot of researchers on this call, just given the organizers. I think for the research community, both in industry, those of us who can publish in industry, and then also in academia, I mean, like, to me, by far the highest leverage thing we can be doing is building very good evals that are so good that when somebody does well on them, it'll be like like evals that are so good that they sort of uncontroversially index progress in that field. So like Microsoft released a really good eval a few weeks ago. It was based on like sanitized incident data, and where the sort of agentic task needs to be solved is actually sort of like doing a multi-hop like series of queries where the agent like investigates the incident and like finds the attacker in like this big haystack of like sanitized data. Like, I think that's a great example. I mean, that's one example. I think CyberGym is a great example also. Like, there's a lot of good evals out there right now, but it's like, that's just like the very start. And like, I guess I would go back to my ImageNet metaphor. I mean, I think ImageNet had like 1,000x the impact on computer vision than any particular ResNet, implementation or like, convolution, and like whatever, any particular decoration on the standard convolutional neural network recipe, because it gave the whole community an operating system for like hill climbing, like the image classification problem, and allowed for an enormous amount of innovation. I think we're like sorely lacking that in the research community, and so I think there's just a lot of leverage in building evals. But on top of that, there's lots of other good work to do too.
Sounds good. Okay, so we can move on to the next question. Yeah, so I'm also curious, like, what do you see as the most critical open research problems at the intersection of AI and cybersecurity? Yeah, Newton?
Yeah, I think that in some sense, the most critical problems are, I sort of, at a very high level, I bucket this into two areas. One, I think is one that everyone is pretty convinced about, which is just, okay, like in terms of capabilities, how can we try to best differentially accelerate defenders over attackers? And I think like that's a sort of like high level problem. Obviously, there's a bunch of sub problems, but I think figuring that out is really important. And then I think the other part of it is exactly this question of actually like, okay, like how can we actually build these what, again, I think we're very aligned with the idea that yes, we need to pursue a line of like autonomous security defenses. And I think that is just an entire, as I'm sure Joshua appreciates from his talk, like that's an entire research roadmap and multiple sub problems on its own. I sort of view these two as again, at a high level, like really the most critical two problems they have to face, and really two of the problems that we're spending a lot of resources internally at Anthropic working on right now.
Sounds good. Okay, Ian?
Yeah, I think right now we're at the phase where we need to just continue to increment on the difficulty of the challenges that we currently are looking at. So going back to my talk earlier, harder evals, more realistic environments, all that stuff. I think there are probably like big research problems that need solving that you could label, but I really think we need to just do a little bit more work first on the complexity of eval data sets first to really scratch at what those research problems are.
Got it. I agree. Joshua?
Yeah, so the question is, what are the most important areas to work on, Eugen?
Yeah, so what do you see as the most critical open research problems at the intersection of AI and cybersecurity?
Yeah. It's such a big question. I don't think I have a very good answer other than
Yeah, it's a really broad.
other than work on evals. Yeah.
Okay. Yeah, and then we have like 2 questions left, and then these 2 questions are like actually our organizers are also really curious about your opinion. And the first question is about prediction. So when do you think AI will surpass the human experts in almost like all cybersecurity tasks? Like I believe that because you are from Frontier Lab and that you already believe that AI will someday surpass the human experts in almost all cybersecurity tasks. But here, this question is more like a when. So Newton, can you start?
Yeah. So, standard grain of salt, obviously, cybersecurity tasks is really broad and all that stuff. I think I tend to be maybe more optimistic. I sort of suspect that I think my median guess might be that we're looking at something like 18 months before we're sort of like really surpassing a lot of what I might consider like median performance on cybersecurity tasks.
Sure. And how about Ian?
I think that AI will supercharge humans' abilities in the cybersecurity domain and will lift up people who might lack a lot of the sophisticated skills required to implement cybersecurity. But at this point, we still think that humans should be in the loop in these cases, and human judgment, ethics, values, etc., are critical to maintaining the stability of our world in general. And so answering the question of when AI will surpass humans, I think it's the wrong question. I think the question should be, when will AI be a far more empowering turbocharger of human ability to defend networks, to make a secure global internet, digital world, etc. And I think we're starting to see that already, but I think it goes back to the question of, how do we get this in more people's hands? How do we expose those capabilities to people? And how do we continue improving the model capabilities? And so I think pushing all that forward will solve the problem of, or not solve the problem completely, but will help address cybersecurity in general and turbocharging capabilities.
Okay, thank you. So then you think human anyway always like should be in the like collaboration with AI to solve the cybersecurity task instead of just like AI only AI as a like autonomous agent, AI just doing the cybersecurity task. Is it like correct?
I mean, there's lots of ways to view a human in the loop.
Yeah.
I think at a high level right now, there's a lot of questions that continue to need to be worked out on how humans engage with agents in this domain, and we still need to figure out the answers to that. So I think it'll be an evolution.
Okay, thank you. How about Joshua?
Okay. A few thoughts. This is a very interesting question. I mean, so for one, like even in cases where, so a few disjoint points. So like one, even in cases where it appears we've achieved full autonomy, like say like Waymo in San Francisco or something. I mean, there's still like operators in the ops center, who are like, there's like a 1-to-10 ratio, I think, right now between like operators and Waymo cars. And then there's also the things that you'd normally expect a driver to do, like get like, I don't know, like change a flat tire, right? Like you still need like a person to come out and do that. So like there's a lot of hidden human labor, even in cases where it feels like we've sort of totally climbed the hill of autonomy. I'm sure that'll continue. I guess to Ian's point, like I'm sure that'll continue to be the case. And really like there's some sense in which like we'll just want to keep sort of like moving that ratio to our advantage, like where like there'll be like a 1 to n ratio and we just want the n to keep going up. That's one thing. I mean, another thing I would say is, yeah, I think this is interesting, like because I think I have a more pessimistic take than Newton. Like, I think that actually maybe not. I'll just say what I think about how close we are. Like, so I'm wondering if other people have had the experience of like trying to get an AI agent to do something like approve access management requests like within their organization, and discover that there's like a local dialect of English that's spoken in our organization that the LLM just like doesn't understand, right? And then so you wind up like tweaking the prompt a million times, right? And then like even when it seems that the LLM does well enough, then there's the sort of organizational friction of like convincing folks that like, yeah, we should turn over this like sensitive decisions like to an LLM, that used to be made by a human. So there's that also. And like that example is for a task that's like highly in distribution for LLMs. It's like basically a document classification task. Like you're taking a bunch of sort of evidence and like having it spit out a binary decision, like should the person have access or not. I mean, that's one example of like where we're at in terms of autonomy. But then there's much more complicated examples, right? Where like, if you really want an LLM to automate what like a code security analyst does, I mean, they're not maybe 10% of the time like they're trying to find bugs in code, right? Like the other part of their time, they're like they're doing like sort of project management stuff, like trying to get people to actually fix the bug. They're like negotiating with like legal and like there's like a whole bunch of other things too, like a lot of hidden labor, right? Like, so I think that makes me a little bit more like, I don't want to say pessimistic, but makes my timelines a little bit longer. And then the last thing I would say is that I think we do, like I said in my talk, like I think we do have the technology stack to actually succeed in automating a whole lot right now, but it's going to take a lot of investment around like developing like high quality fine tuning data sets, like developing evals so we can actually build the technology in a mature way, and build in some cases building RL environments. So it's not that like we need some big scientific breakthrough, but in a lot of cases it's just a question of like how fast the industry is going to actually make the investments in those areas.
Okay, sounds good. Yeah, I agree. Okay, there's a last question, and the last question is, who do you think will benefit more from AI between attackers or defenders in the short term and in the long term? Then could you start, Newton?
Yeah, I think my take is maybe not too controversial. I suspect that in the short term, attackers might be advantaged due to what we might view as like deployment issues. Of really making sure that even small businesses, like Ian was saying, can get access to these types of tooling. But I feel quite optimistic that in the long term, which isn't even necessarily that long, it'll be defender advantaged. And I think a big part of what we as Frontier Labs and certainly Anthropic is trying to do right now is trying to do as much as we possibly can to shrink that timeline of what short term actually means.
Okay. How about Ian?
I think that honestly, I think it's up to all of us. I think it's up to the world to figure out if we are able to use AI tools to patch all the 0 days in code, and like if we were able to do a mass mobilization right now where we patch literally everything, then the world would be a whole lot safer. But that's not an AI thing necessarily, as much as the logistics of deploying it to all these services. So, I mean, this really it's a bigger question than I'm empowered to answer right now, and it relies on political, economic, and human will forces to get done. But hopefully, it'll be defenders. I think there is a path where defenders will largely benefit from this technology.
Okay, yeah. Thank you. How about Joshua?
Yeah, I mean, wildly speculative, right? It's like very hard to predict the future, especially about complex systems like societies. But I mean, I guess like first principles, right? Like defenders have a lot more flops. Like we have a lot more compute than attackers. Like the world's comprised of like, what, 0.01% or probably much less, orders of magnitude less than that, like cyber attackers who are trying to do us harm. Whereas like the whole world's like, runs on compute, right? This is our coordination and comms infrastructure. So we have a lot more compute than the attackers. And if you imagine sort of in the limit or asymptotically, like, having good intelligence, good security intelligence, be ubiquitous, where it lives on every edge device, every phone, it has a small model, every EC2 or, like cloud instance, like has a small model, and they're all able to reason about the enormous haystack of signals that, we need to process in order to detect attackers. I mean, that seems like a pretty optimistic picture for defenders. But, I don't know. It's very, very hard to predict. So, yeah.
Sure. Thank you so much. So yeah, we can end. So thanks again for your great talk and panel discussion, Newton and Ian and Joshua. Thank you so much again.
All right, thank you, Eugene.
So next, I will host today third session. And in this third session, we have three speakers, Dansong, Nicole, and Richard. And the first speaker is Dansong. Dansong is a professor at UC Berkeley and the director at Berkeley RDI. So hello, Professor Dong. You can start your presentation.
Okay, great. Yeah, thanks. Thanks everyone. And thanks again everyone for joining the workshop. Yes, my name is Dong Sung. I'm a professor in computer science at UC Berkeley and also a co-director of a campus-wide center called Berkeley Center for Responsible Decentralized Intelligence, RDI, which is co-hosting this workshop. So for my talk, I'll talk about frontier AI in cybersecurity, risks, challenges, and future directions. So as we are all excited about the fast advancements in frontier AI, at the same time, we also need to be aware of and pay attention to the different potential risks. So for me personally, I do strongly believe that cybersecurity will be one of the biggest AI risk domains for a number of reasons. First, today attackers already have diverse incentives for attacks, and also attacks are already causing huge damages every year. And with increased AI capabilities, it can significantly reduce attack cost and increase attack scale. And the key question here is, how will frontier AI change the landscape of cybersecurity? In particular, given that AI as a dual-use technology can help both the attacker side and the defender side. And in particular, the key question is, who will AI help more, attackers or defenders? And to answer this question, we need to do comprehensive analysis of the full life cycle of cyber attacks and defenses. Cyber attacks are very complex. An end-to-end cyber attack often goes through multiple stages called the kill chain. And defenses also go through several stages as well. And so my group actually has been the first to investigate using deep learning for in cybersecurity domain, such as binary analysis and vulnerability detection. So almost a decade ago, our earlier work showed that deep learning, even back then, can already reach state-of-the-art in certain cybersecurity tasks, such as binary code similarity detection and vulnerability detection as well. Now, fast forward with the advancement of frontier AI, the AI capabilities in cybersecurity has even further improved. In our recent work, we have conducted in-depth analysis where we surveyed hundreds of papers and articles to analyze the current AI capabilities and impact levels throughout the different attack stages, as well as different defense steps as well. And our work showed that the AI impact today are still mainly limited to for attacks on humans, such as social engineering and phishing attacks. But however, with the recent progress, our work also shows that the cybersecurity landscape is changing very rapidly. In particular, given the recent increase in reasoning and two-use capabilities of frontier AI and in agentic AI. So here are two examples of our recent work demonstrating this point, that the AI capabilities in cybersecurity today are already getting to a very advanced level. So the first example is our recent work called Bounty Bench, which assembles a benchmark including 40 real-world bug bounties from 25 diverse web systems. These are real-world bug bounties and real-world web systems where web developers put out these monetary rewards to incentivize white hat hackers to help find vulnerabilities and also develop patches. So with our Bounty Bench evaluation work, it shows that today's agents can already solve a significant fraction of these real-world bug bounty tasks, including vulnerability detection, generating exploits, and also patching the vulnerabilities as well. And these agents can essentially claim the monetary rewards equivalent to tens of thousands of dollars in these real-world bug bounties. So that's Bounty Bench for web applications. So in the second example that I will mention here is called the CyberGym, is another benchmark that we developed recently, including close to 200 large-scale, widely distributed open source software, and included over 1,500 previously discovered vulnerabilities. So we tasked the agents with two different tasks. The first one is to identify previously known vulnerabilities in this open source software, and also to generate proof of concept, POCs. These are inputs that actually will trigger the vulnerabilities, for example, causing the program to crash and so on. And also essentially trigger what's called sanitizers, which can actually detect that the vulnerability has been triggered. So that's the first task. And the second task is to have the agents to find previously unknown vulnerabilities. So essentially also called 0 days, and also to generate the POCs for them. So our work showed that frontier AI's capabilities in these tasks have improved drastically, even just within a short period of time. So in particular, we show that as the new model releases, we see the agent's capabilities first in solving, in finding previously known vulnerabilities and constructing POCs has been improving really fast, going from, for example, Sonnet 4 in the late spring, early summer, was able to find close to 20% of previously known vulnerabilities and generating successful POCs, to GPT-5 actually around for high thinking mode for over 22%, all the way to Cloud Sonnet 4.5. The most recent model release actually reached close to 30%. And these numbers from with just a single trial for these agents. And in addition, what's more surprising is that the agents also have been able to discover previously unknown vulnerabilities, essentially 0 days, and also generating successful POCs for these. And a number of CVEs have been issued by the developers after we disclosed the discovered 0 days, and also a number of these 0-day vulnerabilities have since been patched by the developers as well. Furthermore, so CyberGym has been included, for example, in the system card for the Anthropic's most recent model release, Sonnet 4.5. To serve as evaluation for AI capabilities in cybersecurity. And also, Anthropic's work showed that when they improved the budget, since we had the limited budgets from academia when we run the experiments on CyberGym, but at Anthropic, as they increased the budget, they show that the agent's success rate also improved significantly. For example, when the agents can do 30 trials instead of the single trial as what our earlier work reported, the agents actually can find close to 67% of the previously known vulnerabilities and generating successful POCs for them. And also they are able to find significantly more new vulnerabilities as well, and also generating successful POCs for them. So these examples illustrating that AI's capabilities in cybersecurity are increasing really fast. So the key goal here is that we would like to utilize the AI capabilities to help more on the defense side than on the attack side. However, our recent analysis also showed that there are a number of challenges in this area. So first, our analysis showed what we call the concept of equivalence classes is given the dual use nature of AI technology that can help both the attacker side and defender side. They unfortunately, the same capability advancements for defenses can also often help the advancements of attack capabilities of corresponding stage. So in our work, we provide more detailed analysis for these different equivalence classes across the different stages for attacks and defense. So this illustrates the challenge of having AI help more on the defense side versus attack side, given the dual use nature of AI technologies. And there are additional challenges, in particular due to natural asymmetry between the attacks and defense. So oftentimes there's the following argument. And even I think throughout this workshop, also we hear some of these arguments as well. So, well, some of the arguments says that we don't really need to worry as AI capabilities increases. Defenders can use AI technology to discover and fix vulnerabilities before attackers, and hence we don't need to worry. So is this true or false? Unfortunately, this actually is not quite true. Given the natural asymmetry between attack side and defense side. So for example, offense side only need to find one successful attack that works, whereas defenders actually need to fix all vulnerabilities and prevent all attacks to succeed. So our CyberGym work actually also illustrates this point well. So in our CyberGym work, we analyzed different agents and also with different models, their performance for the tasks that I mentioned, for example, for reproducing the previously known vulnerabilities and generating POCs and so on in the CyberGym benchmark. So what our finding shows is that even though some agents and some models are clearly stronger than others, but however, when we compare the different vulnerabilities and POCs that the different agents and different models finds or constructs, they actually there's not a superset relation in the sense that actually the different agents and different models, they tend to find different vulnerabilities in the benchmark. And so even weaker agents and weaker models, they can actually find some vulnerabilities that were not found by the by the stronger models and stronger agents. So this illustrates that even as defenders spend more resources to try to find vulnerabilities and patch them before the attackers, even when the attackers are spending less resources, the attackers may still actually get lucky and find vulnerabilities and construct successful attacks before the attackers can find them. And there are also other other asymmetries, other reasons why AI may help, may give offenders more advantage than defenders. So for example, cost for defense oftentimes can be much higher than attacks. Deploying defense, even when it works, can take a very long time. One needs to develop the patch, needs to do a lot of testing for the patch, and needs to deploy the patch globally. So for example, a lot of legacy systems today are still not patched, even when the patches have existed for a very long time. And there's estimates that the current mean time to deploy remediation in hospitals takes close to 500 days. And furthermore, as our work more than almost like 2 decades ago, and also others' work have shown that attackers can even learn about vulnerabilities and generate exploits using public information on patches, and then can exploit systems before they can be patched. So attackers doesn't even need to go find 0 days themselves. They can just take public patches to generate exploits and exploit the systems that haven't been patched. So this is just one example of asymmetry between attacks and defense. And our paper also actually goes in more detailed analysis and demonstrates other types of asymmetries between attack side and defense sides as well. So for example, attackers have much higher tolerance for failure, whereas defenders have much lower tolerance for failure. And attackers tend to prioritize scalability over reliability, since they just need to launch large-scale attacks, and even if only a small fraction of them works, it can still be a win for the attackers. Where for defenders need to prioritize and focus on reliability to ensure that the defense system mechanisms are robust and works even when there are no attacks. So given the challenges and given the fast increase in AI capabilities in cybersecurity, it's very important for the whole community, for us, to do continuous monitoring of the enhanced AI capabilities in cybersecurity, and both on the attacker side and on the defense side. And to address this challenge, we recently have launched what we call Frontier AI Cybersecurity Observatory to serve as an open platform to bring together relevant AI in cybersecurity benchmarks, and to bring the community together to do continuous monitoring for AI capabilities in cybersecurity. And CyberGym and Bounty Bench are good examples. And also, our analysis showed that there is a wide gap still in terms of the benchmarks that are needed to have broad coverage of the different attack stages and defense stages for to evaluate AI capabilities in cybersecurity space. So we welcome the community to come together to build out more comprehensive real-world, realistic benchmarks, and to do continuous monitoring of AI capabilities in cybersecurity. So given the challenges that I mentioned, there's a key question: how can we actually then help AI to shift this balance, to have AI to help defenders more than attackers? So in my own personal journey for the past over 2 decades of research in software and cybersecurity, as well as the security community overall, we have gone through several paradigm shifts in terms of developing defenses. Initially, it's a reactive defense, where defenders focus on detecting existing attacks and try to block them, such as detect malware and block these malware attacks. And then it shifted to proactive defense through bug finding, as what I mentioned earlier. And then finally, to the final paradigm, the paradigm through proactive defense through secure by construction. So in our paper, we also did a detailed analysis showing that the first defense paradigm, reactive defense, it can still help, in this case, AI can still help attackers more than defenders for a number of reasons. Given the interest of time, I won't be able to go into. And also, as I already explained, for the second paradigm, proactive defense through bug finding, here AI can still help attackers more than defenders in the near term. So we hope that to really help to shift the balance, to have AI help defenders more than attackers, we can enable the third paradigm, proactive defense through secure by construction. So in this paradigm, secure by design, secure by construction, this paradigm focuses on architecting and building provably secure programs and systems. This approach is in contrast to bug finding and attack detection and reactive defenses. And in particular, using program verification, this approach aims to provide formal proofs that a program or system satisfies certain security properties. And using this approach, we can provide provable guarantees of security properties of the programs and systems, and that can actually help eliminate entire classes of security vulnerabilities. Given the power of this approach, actually, largely thanks to the efforts from the formal verification community, we have entered the era of formally verified systems, where there have been many different systems, including microkernel, file system, compilers, and so on, that have been formally verified. However, these systems have now been largely deployed in the real world, mainly due to the issue that it's labor intensive to actually do the formal verification. Oftentimes, it requires tens of proof engineering years. For example, in the case of SEL4, the formally verified microkernel, to do this formal verification. And when the code changes, then the proof needs to be changed as well. In order to address this challenge, my group with collaborators has been among the first to use deep learning to help automate theorem proving. So, for example, in the collaboration with Ilya back then at OpenAI, 6-7 years back, we showed that using deep learning techniques, even back then, it can help improve certain steps for automation in theorem proving. And now, fast forward, given the advancement of frontier AI, I do strongly believe that we are hitting an inflection point. In our recent paper, we lay out a roadmap to bring the community together to enable to further develop frontier AI to enable formal mathematical reasoning and program verification. And using this approach, we hope that we can develop AI agents instead of just playing games like Go. We can actually automate theorem proving for program verification. And when used in conjunction with program synthesis, we can, instead of just generating code, which has no security guarantees, we can actually now generate provably secure code. And today, people are really excited about coding agents and AI-generated code. And more fraction of the code is generated by AI. But however, how safe and secure is AI-generated code? With our recent work and also others' work, we show that today's AI generated code can be vulnerable. Today's AI models can generate highly vulnerable code. To address this issue, we propose, instead of just generating code with no security guarantees, instead we can generate a verifiable code generation. Where given the task description, we can generate code and also generate specification, and also generate proof that the code actually meets the specification. In our recent work at Verina, we developed a comprehensive benchmark on verifiable code generation. And with this benchmark, we evaluate that today's agents are still not good at generating proofs and also not good at generating specs. We hope with the further advancements of frontier AI, we can develop AI agents with much more advanced capabilities to enable this generation of both proofs and specs, and also together generate provably secure code. So of course, there are many challenges remaining still for this approach. Given the issues of time, I won't go into this, but we hope that with the community together, we can work together on advancing in this direction. So overall, to just summarize, there are a number of lessons. We hope that throughout this talk and also this workshop, that people have learned. So one, AI capabilities in cybersecurity is increasing drastically, and we are really hitting a pivotal point. And also from our analysis, it shows that AI can help attackers much more at the beginning than defenders, especially given the natural asymmetry between attacks and defense. And as cost of attacks going down, we expect to see unprecedented increase in attacks. And as what we are seeing today, already attackers are using these are using frontier AI already to advance their attacks. And the world was not prepared for the pandemic, such as COVID, despite early warning, and attacks with assisted AI could be much worse. And here I just wanted to briefly share some of lessons that we learned from my earlier work in the domain of medical device security. So my group, together with collaborators, we conducted over almost a decade and a half ago, we conducted the first medical device security analysis in the public literature, and showed that back then certain medical devices had critical security vulnerabilities. And back then, FDA's medical device approval process didn't even mention security. So only a few years after following our work and others' work, FDA then issued guidance recommendation on medical device security. So from this lessons we learned is that security space is complex, and frontier AI will have huge impact in cybersecurity, with a significant increase in attacks that we are seeing today already due to Gen AI, and also in the near term, AI can help attackers more than defenders. And hence, it's important to learn from the past lessons and act now. We need to build and deploy plans to improve security posture and get ready. And also, we need to use AI to build secure systems with provable guarantees. So with that, I just want to conclude that we hope that as future directions, the community can come together to build resilience, and we need to start building resilience now. For example, as I already mentioned, and also in our analysis, we show that the current landscape for benchmarks and evaluation in cybersecurity is there's many gaps, and we hope that the community can come together to develop more comprehensive benchmark evaluation for AI capability in cybersecurity, and do continuous comprehensive marginal risk assessment. And we hope that the community can contribute and work together to build this Frontier AI Cybersecurity Observatory. And also we need to enhance defense development, in particular to enable probable security through AI, including verifiable code generation with probable security guarantees. And also, for example, approaches such as automatic translation of C to Rust to provide memory safety as well. And we also need to develop new approaches to mitigate human-related risks as well. So with that, again, we hope that the community can join the effort together on building this Frontier AI Cybersecurity Observatory. And also, I just want to quickly mention that also we are hosting the Agentic AI MOOC, Massive Open Online Course, with over 32,000 enrolled. You can learn more at the MOOC website, agenticai-learning.org. And we're also doing a competition this semester on Agent Beats competition for agent evaluation with over $1 million in prizes and resources. With that, thank you.
Okay, thanks for Professor Song's great talk. And due to the time limit, we have one general question. So I read your amazing paper about the definition of AGI. So I think that's very interesting. So I think many audience also want to know the question. So how do you think how many years we can achieve AGI?
I see. Okay, that's a very good question. I think so. With the recent AGI paper, we try to at least lay out some concrete definition and metrics for AGI, and it's really right. It's not meant to necessarily be definitive answer. It's more, I think, as a starting point for the community to come together to develop more concrete and also common knowledge that we can discuss together. And with this, so in the paper, we also, provide some evaluation of along the different dimensions in AGI. So of course, it's difficult to predict when we'll hit the points, but I think there is overall there's a lot of a lot of the groups. I think in general we do predict that within the next few years,
Okay.
the AI capabilities can increase drastically. That can make a huge difference.
Okay, thanks, great. That answered my question perfectly. Thanks, Professor Dong's great talk. So our next speaker is Nico Landers. And Nico Landers is a co-founder and CTO at Dreadnode. And hello, Nico. Nico, you can feel free to share your screen and start your talk.
Excellent. Yeah, thank you for having me here. I thought I'd start with a quick intro. My historic background is in security as a career. So I did malware engineering, capabilities engineering, a lot of technical work on the offensive side, but blended it a lot with software engineering. And so the talk I want to take us through today is really going to cover my perspective on how software engineering principles maybe overlap in this new agentic space, but even more broadly, maybe patterns I've observed in the way people apply new and novel technologies as they relate to software in the security space. So my current day-to-day is primarily building capabilities, frameworks, and platforms for applying LLMs and AI technology to the cybersecurity space, specifically on offense. So my premise that I'm going to work with through the talk is that we're at a place now where obviously these models have been proven to be able to do the thing, whatever the thing is. A lot of people measure as like code security, could be agentic offense, solving CTFs, doing some like general analysis, assisting with reverse engineering. And the problem space we're moving into now is whether or not we can do this process reliably and at scale. And my premise is that this is actually an infrastructure problem now, not so much a skill set problem, or even a problem that's going to be solved just directly by model improvement. I think that point's been made pretty broadly, both by the Frontier group and the AIxCC group, which is that like the harnesses that leverage these models are actually becoming more and more relevant now. And the delta in performance is going to be driven largely by them as opposed to anything else. We also care a lot about just measuring the broad capability now. So does it actually do the thing in the real world? I think Newton from Anthropic made a great point there of, you start with evals and benchmarks, and then at some point you graduate to just caring about, in this scenario that is as close to the real world as possible, how does the model perform end to end? So when I was doing a lot of malware engineering, I taught courses on how to do malware engineering, and a pattern I saw in the space was a lot of security people, a lot of very technical ICs are really interested in the idea of writing malware because it felt like this kind of esoteric, or maybe not esoteric, but this very like specialized piece of software that was aligned with their domain expertise. And they would all start down this road of writing a piece of malware. And then as soon as they arrived at the moment where they realized it's software, it got uninteresting to them. The software itself is just framed by intent. So C2 software has almost 95 shares 95% of its core capabilities with like a remote management software you would use for IT. And when you are an individual contributor or domain expert writing specific tools for your use case, you can oftentimes miss out on like bigger context, like larger context from the software space. And there's also this pattern from security where people working on these problem sets, building the software, were very technical individuals rewarded for their deep technical knowledge, as opposed to like architecting broad systems or maybe playing in this bigger process of engineering itself. So I see a lot of similarities here with the agentic software space, where there is a broad incentive to work from the bottom up with your specialized expertise. So maybe you've spent a lot of time with these models, you're really familiar writing prompts, you think about agentic systems, and you've maybe written a framework for it. And you take every novel idea you have, give it a unique label, and then kind of compete on this stage to say, I engineered it this way, and the way of engineering an agent in this multi-agent system is labeled as X, and X is the best way to do it as measured by this benchmark. But in traditional software engineering, we just do this silently. Software engineers have built the entire ecosystem around us purely off of leveraging lessons historically from each other and trying to use like shared terms and a deep understanding of what is actually going on in the system as opposed to the task-specific application of that system. So to give an example, like a container scaling system works the same whether or not the containers are doing medical operations or supporting chat apps or building games. It's a containerization system. So we find these common terms and we try to frame them as software. So what I want to take us through is this idea that eventually where we're going to end up is stochastic software systems, where we treat the systems like we would a model, and we put them through an ML ops pipeline and effectively have the software self-optimize and discover the best way to present itself. So the layout I want to kind of work through here for the mid part of the talk is, in this stochastic software situation, you have these blended components. So I've kind of highlighted like the orange ones here as maybe being the what we would call like more agentic systems. They're portions of our software stack where we've yielded control out to an external stochastic model. Obviously, the stochasticity is something we care a lot about. We want the system to have emergent properties because of it. But in a big picture, really what we're just engineering is software with some like novel edges. So in traditional software engineering, we don't necessarily have to deal with non-determinism, although it's a common byproduct. And we also don't typically think about writing software for use in downstream learning, which is something you do a lot in model building. So you think about the data the model is producing as something that you're going to use later to improve the system. I want to draw some analogies here for software engineering concepts into this agent space. One of the biggest lessons you learn really early on in software engineering is that modularity and the interop between components is extremely important. We have a huge amount of our technical space dedicated purely to designing these interfaces. Not only are there standards, but there's mechanisms we put in place like API schemas and expectations software can have about how it's going to pass data from one unit to another. And I sort of posit that the AI space, the LLM space slowly being brought into more advanced software architectures has been echoing that flow. So the models themselves are text generators. They complete text token by token, and we start stacking on these higher order systems like parsing, role mechanics, structured outputs. We give the model the concept of a tool, which really is just an API schema. It's like a structured format. We start putting them into actors and putting them into distributed systems. But like this is the natural flow that we went through with software as well. Most production enterprise software that you would use day to day, like SaaS applications, run on highly distributed systems that scale. They're containerized units that negotiate with each other through shared API interfaces and message buses. So like we don't need to invent new terms to describe these systems. And I also think there's a lot to learn about this overlap of like the path we are walking in this space is the same path that software engineering has walked previously. When I think about the units inside of this blended pit of software, the software analogy would be a function typically, oftentimes in workflow orchestration, they're referred to as tasks. But the argument I want to make is by small extension to traditional software, we're really thoughtful. We can start to think of these individual units as a small block of logic that in some cases will be fixedly defined. So it's software that we write via code. In other cases, it's a stochastic system where the internal behavior is going to vary every time we call it. But what we care about is taking inputs that we're going to put into this logic block, capturing outputs, and ideally measuring those outputs as well. And once we design the whole system around these unit blocks, then we can start building higher order mechanisms that are really powerful. I want to double click also on the idea of evaluating these unit blocks at point in time. So taking measurements in this system where we want the stochastic software to be part of an MLOps pipeline demands that the measurements we take are imperative. So they are defined wherever the task is defined, and we place them together. And so every time that unit of work performs logic, every time it takes an input and produces an output, we're keeping that as like a row in a data set. This is the alignment that's going to get us to the improvement process later. Sometimes we walk around to this idea by designing, say, RL environments where the scores and verifiers are kept at the environment, and we think about the actor participating in that. My argument is that having these evals in the loop is a really important part of also applying these agent systems to the real world. So in the real world, the things you find, the novel things you find, like a vulnerability in a system that wasn't previously as part of a benchmark, as long as you measured it and you've taken that as a unit in a data set, you can then turn that and feed it back into a benchmark. So we're starting to build and blend the idea of benchmarks with like real world actions. So the actions your system takes start to become data units you learn off of and also you benchmark off of later. If I take a single unit and imagine it's stochastic, so I'll assume it's running like a really simple agent React loop, then the challenge we have is that this function is relatively black box. We can think of it like a code function, which is that it has like an input interface and an output interface, but the interior logic is going to be determined by some model. And that model, the way we control that model is really relevant. And the way we get insight into what's going on in that black box is also super relevant. So in systems we build, we like to present a state that goes into this box. In the case of LLMs, it would be like a list of messages and events that occur during the execution of that sort of logic unit. And these events can then get fed out to external systems and be reacted to. And once you have that, you start to plug into a bigger software architecture where you have like actors or units sharing a message bus, where the code that's measuring the output of a task or the code that's reacting to the behavior of an agent doesn't necessarily have to be co-located with that agent, which is going to be really important when we start to plug these systems together and scale them up. In software, we have a really powerful like tracing subsystem. We all maybe familiar with like OpenTelemetry, and this is starting to get applied to the space, and that's not by accident. Ultimately, if you have a piece of stochastic software where portions of it are relatively undefined and their behavior is going to be dependent on parameters you place in, then the trace that you collect out of that system, the trace of the software stack is in some sense everything from a trajectory to your data set. It can be converted later or thought of later as any of the important data units you need to facilitate active learning on this process. So I mentioned here that like computational graphs are inherently DAGs, so oftentimes we get confused. We think of building agentic systems and we think of building workflows, think of workflows and we think of DAGs, but it's like writing software is implicitly a DAG. There's a flow of execution that we can capture, and ideally this execution is imperative as opposed to declarative, so that we can let the software do the things that software is great at, which is be a dynamic system that's responding to input data without having to fixedly define all of its behaviors, which is a rather immature way of viewing software architecture. In terms of improvement, once we have these units defined, we can think, especially for the agentic units, as taking in some combination of context and a model pairing, right? Those are really the two inputs that define the behavior. I maybe think if there's some analogy here of like source code. It's like a fuzzy bit of source code that we care about. And context engineering as a term, I think, has emerged because people have started to understand that that is your control plane. Like the context going into these units in terms of all of the tools and higher order elements you have being distilled into like a set of text that's going into this inference model is the way you can influence its behavior. And so controlling that's really, really functional. And even more than that, once we have that control surface, we can start thinking about all of the alignment between the improvements, like the optimization strategies and post-training processes we apply to these units of work as being a really cohesive story about their operating on the two core elements that define the behavior of this unit of work. And so these are really powerful elements that should be generalized. We shouldn't think about wanting to do optimization and then build a system around it. We should build the system in such a way that we immediately have the levers to pull during this training and optimization process, and those are well defined. We can do this partially by all the magic that code has to offer, where we can take like very rich objects that have like nested elements and kind of get a whole visualization of what is about to be a dynamic stochastic piece of software and extract out a bunch of parameters and configuration values that become the knobs we turn. And I kind of think of this as like taking elements from the software and turning them into hyperparameters that we can optimize against. To speak more specifically about some elements here, this has been mentioned, I think, in AIxCC, most notably. The tooling layer in the cyberspace is like really potent to us. I think wrapping these complex tools and exposing them as if they're an API, particularly the way we want APIs to work, which is like kind of stateless and very well defined, is very hard. These tools are super disparate, and my focus is almost exclusively on the offensive side that doesn't include the defensive side and a lot of supplemental tools there. I think software engineering is a very mature space by comparison in terms of the tools being extremely well defined and the tools being highly optimized to be relatively consistent in their behaviors, because that is how we construct useful software. And so a pattern we can use is treating this tooling layer, the manipulation of it and the layout of it, as another thing to optimize against. So this is a chart on the right of network operations agent that we're having run against the game of Active Directory Go environment. And you can see here, I'm looking at the score deltas when I pass different types of tooling interfaces for the same set of underlying tools to the model. So this is like a network ops agent, and so they'll have a CLI tool, and we get to choose whether or not we want to expose like general functions or specific functions, whether or not we want to constrain documentation of the tool or only give it a subset, a small aperture into the tool, and all of those can affect performance. We also care a lot about, as mentioned up at the top, just the scalability and general reusability of the tool sets, which in cyber are usually very poor in this sense as compared to software engineering. From an environment side, and this has been talked about a lot today, cyber environments are very tricky to reproduce. And I think the core reason of this is that a cyber environment, like cyber is an intent. Like what we do in security is we test integrated systems. And so by definition, when we mean cyber environment for the majority of use cases, we're talking about deploying full integrated network stacks and applications, because there is really no definition of a dedicated cyber task, maybe outside of some code analysis tasks, right? Like if I want to write an agent that is good at network ops in a Windows Active Directory network, another way I might frame that question is, can I build an agent that could manage an entire Active Directory network? What would the environments for that look like? What would the evals for that look like? And that's true for every subset of cyber. So Josh's slide where he kind of showed like all of the buckets of the variance in cyber is just going to dictate that these environments are extremely complex, difficult to build. And maybe in a sense, I'm more keen to just get straight into the real world as opposed to focusing too much on reproducing the real world through an environment, because the real world is already an environment. We maybe don't get the cleanliness of an eval in order to like reset state and kind of manage the noise in the environment. But hacking a real world app on a bug bounty is a free environment. Like that's an environment that is public that you can access. And it maybe doesn't conform to the mathematical or RL version of an environment, but it's where we want these agents to work anyways. And then the place I'll kind of finish on here is the idea that this system should be built with scaling in mind. There is a huge overlap. There's a talk from the PyTorch conference that actually Don did a keynote for, and I can't remember his name, but an engineer from Anyscale is talking about how despite the fact that there's a huge variety of RL frameworks, they all share Ray as an underlying scaling mech. And so you can see that like, despite them wanting to express all of these disparate opinions about what an RL framework should be, when the rubber meets the road in terms of infrastructure, they're all relying on really mature systems to get stuff done. And I don't think we should reinvent the wheel there either. The target state that I'd like us to get to finish this whole thing off is that we have a platform, and the platform backs observability and the artifacts we care about and manages a cluster of capabilities that are deployed at scale. And as those capabilities run both in evaluation modes and in the real world, you have this data flow back into the central platform. And we treat this whole software architecture like we do models, which is that I have a unit of capability that I can deploy and I can version. I can gather data from it and I can take it through a training process or an optimization process later and effectively hill climb on the whole thing. And all of these problems are actually well solved in software. And I think we should lean more on thinking about the agents we're building as both units of stochastic software, but also how they plug into systems we're already familiar with, like model inference, platforms, and AI infrastructure. And that's it. I hope I wasn't too over. I'm 2 minutes past, I think.
Hello. Thanks for Nick's great talk. Yeah, maybe we can have one question due to the time up. So, do you think when will AI models surpass human in cybersecurity tasks? That previous speaker was discussed that.
Yeah, question of the day. For us, they already have in quite a lot of subsets. I mean, an agent in our environments can hack a network in minutes that would maybe take me hours. So depending on the skill set, that's kind of already passed. And to me, the question becomes less about are they better than humans and more about how are they facilitating a process. I don't look at a piece of software and ask, is it better than me at a task? I look at the software and think about its application to a task set and a process and a team. And so I think maybe a maturing perspective for me would be like thinking of these agents as being human capable is less relevant than thinking about the systems that we build them into and those supporting like an activity or a workload we care about. And so I think the software complexity is going to define a lot of how quickly we scale that into the future. And the real world application of these systems will start to deviate more and more from benchmarks as it depends more on how people engineer the software than it does the raw capabilities of the model.
Right. Thanks. Okay, so due to the time limits, we can move to next speaker, Richard Danzig. Yeah, Richard Danzig is a senior advisor at Johns Hopkins Applied Physics Laboratory and 71st Secretary of the Navy. Hello, Richard. You can feel free to share your screen and start your talk.
Yeah, of course, I've got now a system setting challenge. I was going to say that the world that I'm seeing is very like the world that's been described up till now, the rapid advances that occur. What I particularly want to stress, though, is that the points that Ian made when he talked about the models can do so much more than we're actually implementing in reality. And Josh's point that a critical variable in this regard is the process and not just technology. Those points are fundamental to what I want to say. I'm not concerned with the small companies so much that Ian talks about, though that's a very legitimate concern. I'm at the opposite end of the spectrum, thinking about the Department of Defense, and I want to use it as a kind of case study. And 4 themes run through this case study. First, the fact that really the problems are not just problems of development, they're process of organizational assimilation is a fundamental issue. And there's huge organizational, this is the second theme, resistance to these changes. That resistance is actually shaped by distortions that in organizations that, in my mind, are very like responses to weights in AI models. The organizations have vectors as a result of their own organizational weights as pre-programmed. You can see this even in corporations like the AI world that we're dealing with the Frontier Labs. Google and OpenAI and Meta are all very different because in part of the kind of corporate weights that are hidden behind the scenes. And finally, my fourth theme is one of coevolution. The governments the future of governments will be shaped by AI. I think you all understand that, but I would emphasize as well that the future of AI will be shaped by governments. And it's the co-evolution of these two systems that I think is particularly important to grasp, not just the technology within itself. This is a sort of phenomenon of, as AI meets governments, an irresistible force. AI meets an almost immovable object. So what happens? Eventually, everyone gets there. Eventually, there's no question that there will be absorption of AI systems and absorption of cybersecurity in ways that make all that work. The question is how fast you get there. And there's a classic example of this in military matters, familiar to you all, and that's Blitzkrieg. The Germans take the combustion engine and the radio and the airplane, and they combine those three things in a new form of warfare. But what's so striking to me is that everybody has the combustion engine, the airplane, and the radio. The French have it, and they build the Maginot Line. It depends really not only on the technology, but obviously, crucially, and this is the point that Ian and Josh were making, crucially on the absorptive capacity of the organization. If you don't have that absorptive capacity, you wind up, I think, having extraordinary difficulties in getting where you need to go. The nation states now look on AI, in my view, rather as the nation states looked on the New World in 1500. They understand that this is important. They understand what's going on matters to their futures. But they have visions of it that are akin to, oh, there must be a fountain of youth somewhere where there's a Northwest Passage. They project their own competitions into that new world, and we'll do that with respect to AI. The next slide. I think if you look at what the Pentagon is doing, it's essentially caught up, I think, or not the Defense Department generally, in three aspects. One is a tendency to think AI can now be used to improve our ability to do the traditional things, to augment our capacities to find targets or do intelligence. And at some magical point in the future, everything will be different because we'll reach a stage of AGI or superintelligence. A second thing is that those organizational weights that I talk about translate into thinking about domains of combat. And so the tendency is to say, well, there are 6 domains. There's air, sea, undersea, land, space, and cyber. And the problem with this is that the 5 first domains all have an advocate for them. The Air Force, the Navy, etc., the Army, this newly formed Space Corps. Cyber does not have such an advocate within the system. And AI as a related phenomenon doesn't have something that then is generating both an argument for it in budget context, but also a career path for people who are skilled in it. If you're particularly skilled in these arenas as a young officer, you get a huge amount of disproportionate responsibility, and it's terrific from a standpoint of the individual. But then you get told if you really want to advance in this arena, you need to stop doing it. And for example, in the Navy, go to sea where there are no such billets. So we undermine both the budgetary support and the expertise in these regards. And then the Pentagon inclination is to say, well, we'll receive this as some product that we will then utilize, which dampens the ability again to understand how to integrate it and to argue for it. So the next slide. Um, um, yeah, we got to go forward, not back. It's very tricky. The next slide says essentially what's happening in AI that I think is so important, and all the speakers have referred to it, Dawn particularly substantially, is how the cutting edge of much of our achievement is in coding. If you look at code forces and other measures, what we find is that there's a greater immediate sophistication and aggressiveness about the use of these LLMs for coding capability than many other areas in the space of development. And that's important generally because it points to the extraordinary possibilities associated with recursive self-improvement if this can be harnessed to the development of AI itself. But specifically for this presentation, what I want to emphasize is that that speed of development that all the speakers have touched on is fundamental for cybersecurity itself. And cybersecurity is changing very importantly. And this is the way in which it is received or not inside the organizations that need to adapt to this is important, critical unto itself, but it's also indicative of what this new world will look like. The next slide. Thank you. I just want to emphasize that this isn't a matter of waiting for AGI or superintelligence. And to my mind, it's the automation of standard professional intelligence. And to me, in some respects, this is analogous to Ford's assembly line for making automobiles, except instead we're producing software. What made the assembly line for Ford so remarkably important was that it proceeded 8 times faster than its predecessors, and combining hardware, et cetera, and with that and a new organizational technology, the assembly line, you began to get something quite different than had ever been seen before. It's important to me from a national security standpoint because when you get to World War II, the U.S. capacity to have that automation in Detroit and elsewhere undergirded all the capacity we had in that military conflict. And I believe that our ability to do the same with software will be extraordinarily important. There's a good book on the World War II experience called Arsenal of Democracy. And if you think about that arsenal as software in a world that is dependent on software, where all the different other domains, the ability of our ships to function, our airplanes to fly, our spaceships, et cetera, to operate, all these things are dependent on the software systems. So if our cybersecurity systems are inadequate and can be overwhelmed, we're extraordinarily vulnerable. And conversely, if they're strong and we can automate software better than others, we can protect it better than others. And for that matter, if we can generate offensive programs that are more effective than others, we have a huge advantage. Next slide. So there's been a lot of discussion about defenders and offensive advantage. I'm not going to spend much time on it. I just want to say that a colleague of mine, Chad Heitzenreiter, I thought phrased this well when he went back to a classic article, Anderson's 2001 piece on why information security is hard, and used a rough estimate of 5 errors per 1,000 lines of code. A code base of 25 million lines of code would have 1,250 vulnerabilities. the points that Dawn and others have made, Tyler and Newton amongst them, that you've got such a large base to defend. It's a big problem. It's reminiscent, says Heisenrader, of the Wild West, where the defender difficulties were in developing the time and the cost and the knowledge to be able to create enclaves of protection, but they couldn't protect the whole area. In the long term, Heisenrader and others on this call have argued, I think correctly, that for this reason, when things become automated, they actually function better for defenders than for the offense, because the defenders just had so many things to do that now they can do better. It doesn't mean they'll prevail, but the net addition of AI to that world is I think in the long term more positive for the defenders. But there are two critical qualifications. The first is they have to assimilate it. They have to assimilate it fast. And if you're a utility or whatever, and this software investment doesn't figure into your weight base, or you're terribly worried about what the effect is of modifying one form of cybersecurity, modifying one piece of software to protect it better, but it's interactive with others and you don't know whether it brings down your whole system, you have a strong predisposition to be slow and reluctant. Dawn's 471 days for hospitals reflects that. But the second thing that is striking to me, and the next slide shows it, is that, I'm sorry, go one more slide, if you will, is one more slide forward, one more, that's it, is that there's an exceptional first mover advantage. If you are ahead of others in your adoption of the automated system, you have the ability to defend yourself better than the attackers can manage, and you have the ability to implant offensive capabilities that diminish their ability to attack or their inclination to attack. So your first mover advantage can be extraordinarily great in that regard. So I just want to go back one slide and suggest one way you could use that, for example, that Dawn talked about at the end of her talk, but hasn't featured in earlier talks, is the use of formal methods. There's been a number of pieces of work by DARPA on how to develop formal methods. And the basic idea, well articulated by Galois and the website I note there, Galois being a company that's been very involved with formal methods, is that you can start to, Galois' example is, figure out the size of the hypotenuse of triangles by looking at large numbers of triangles. But if you can mathematically assess what the formula is that would calculate that, then you can cut through all of the particulars. Formal methods provides a mechanism for establishing reliability independent of the actual modes of attack. And it is being used by Amazon Web Services under the heading of automated reasoning. DARPA demonstrated it in this program, HACMS, on helicopters and the like. I've been very keen for RAND, where I'm a trustee, to invest in this area, and it is beginning to do that. Most notably, Kathleen Fisher, who ran the DARPA Information Innovation Office, has moved to RAND to try and develop this program. And I'm hopeful that Kathleen will be speaking at the next version of this session. So if we can go to the next slide and then the slide after, thank you. One more. Thank you. I want to take, just to illustrate this in my closing minutes, the idea of the improvements that are brought by AI to offensive capabilities. The ability to discover vulnerabilities is very great. And the capacity in that context to do reconnaissance and other things is substantial. But in the end, you also need something that is very context rich which is the ability to design exploits to harness together several different forms of attack and the like. And that's a messy environment. It's a long task, and we know from our analyses that AI is not so good at long tasks in these contexts. Next slide. In addition, if you're going to do some attack on some country in their military system in order to embed something that deters them from attacking you, you're going to need rich data about that situation. And AI systems obviously normally profit from that rich array of data, but we don't have that rich array of data in other circumstances. There's also a different kind of alignment problem that makes it hard to delegate to an AI system. A lot of the time involved in these things is deciding what are the competing equities. One enterprise in the government thinks, well, I can get good intelligence information. Another enterprise thinks that thinks that it's better to embed and not harvest the intelligence because there are opportunities, potentially in the case of warfare, it should be kept for potential sabotage. Other entities are concerned about, does this exceed the bounds of what is proper for us to do? Does it target civilians? Is it proportional and the like? These are political judgments that need to be made by humans. So the exploit dependency in these cases requires an interaction between the AI system and its technology and the humans that creates a bottleneck, if you will. So we need to develop in advance, if we're going to harvest the benefit of the AI system, we need to develop that human expertise and these processes, a word that Josh used often, need to be improved to adapt for this, and that's critical. Next slide. So I've talked about the first mover advantage first, but I just would suggest to you, if you translate that into Defense Department stuff, you have extraordinary consequences from having that first mover advantage or not. So next slide. I worry about whether we're well positioned to be first movers or not. I worry that there isn't enough intimacy of relationship between the US government and the frontier labs developing these things. We need early access to the government for the government from these for these things so they can see it coming. And we need US government capacity in terms of expertise, the human capital, et cetera, leadership culture, and improved structures and processes. Above all, we need a much more robust integration as well, or maybe not above all, but in addition with the private sector, as for example, in my example of utilities, you can't, or the banking system, you can't let those be at arm's length as everything else is changing. Next slide. I would just emphasize in conclusion that these are not, in my view, huge step functions. They are not dependent on the coming of AGI or superintelligence. There's a kind of continuity here where there's incremental steps and improvements, as various graphs already shown today indicate. AI and AGI are not the messiah sweeping away everything before them. Rather, what we need to do is build this co-evolution, this codependency that I've talked about. And next slide. The eventual question I'm suggesting is that everyone will get there. The question is, who is the first mover and who is a fast mover? I wrote a paper on this, and I ended it by saying that this is not a wake-up call. People understand AI. The message is we've got to get out of bed and actually preparing for it. And as my last slide, I just want to show you, for those of you who are interested in hearing more or reading more about this, I published a paper in July that articulates most of this, hopefully without the technical glitches I manifested in presenting the briefing. Thank you.
Great. Thanks for Richard. Great talk. So we have just one question for Richard. So as you say, the AI is becoming stronger and stronger and the large language model very powerful. So what do you say the challenges that we face? especially in national security. And how can we do that? What strategy we can do that?
Yeah, well, I think defense over time has the advantage for the reasons I've indicated. In the short term, or let me put it differently, I think that I emphasize the formal methods possibility because I think that historically the big problem with formal methods has been that it doesn't scale. We can show that mathematical proofs work well for small systems. AI, with its theorem proving ability and its processing ability and the like, should open up for us the ability to scale much more powerfully. So my intuition is that that's a path that I want to see more investment on than we've had up till now.
Great. So thanks for your answer. So next is a third panel discussion, and Nico will host that, right, Nico?
Yeah, thank you.
Yeah.
Thank you,
Nico,
Richard.
yeah.
That was a great talk. Yeah, I suppose there's been a couple of questions that have been top of mind. I maybe will lead with the question to Dawn, which has been asked a few times, but where are your current thoughts on AI's ability to surpass human capability? And maybe as a nuance to that, how has that changed over time? Like you've been in the space for a long time. Obviously, maybe 5 years ago, people had, or you had your own opinion, but how has that altered and where do you sit today on the accelerative nature of it?
Yeah, thank you. Yeah, this is a very good question. And I agree with, in some sense, some of the earlier speakers' points too. I think on one hand, yes, right. I think in some sense it's important to know, right, the increase of AI capabilities in cybersecurity. That's also why, as I mentioned, we had launched this effort on Frontier AI Cybersecurity Observatory to do continuous monitoring of the increased AI capabilities in cybersecurity. So to that, I do, right, right, as I mentioned earlier, as our work and others' work have shown, the AI capability in cybersecurity has been increasing really fast. And it is, I mean, right, there are different ways to look at it, right? So again, for example, for these 0 days that the agents were able to discover and generate POCs for in Cyberbench, I mean, these are, large scale, widely distributed open source software. One has been fast tested over a long period of time already, and also there have been a lot of human experts that have looked at this code, on these software programs and so on. So in some sense, right, with agents actually now spending a lot of money, like it's very low cost to find these 0 days. It's already showing that these agents can accomplish things that even human experts have difficulty in achieving. But of course, because also AI models, this is jagged intelligence, so they can be great at certain tasks, and then also, of course, there are other tasks I think that human experts can do that agents still cannot do today. So I think it's right. So the answer to the question, I think, is more nuanced. But that I think that's one dimension in terms of we want to measure AI capabilities. But on the other hand, I do think you're right. Going forward in the future, in terms of the actual impact, is also important to see how human and AI combined, how they can actually achieve even greater greater capabilities and greater impact. I mean, this I think has consequences both on the attack side as well as on the defense side.
Dawn, if I can get in here, Nick, is it okay if I comment?
Please.
I think there's one respect in which I think the debate about superintelligence and even more about AGI is not helpful and misleading. And there's one respect in which I think it's extremely important. The debate about that's misleading, I think, is to me, intelligence is spiky. It's not like there's one uniform kind of superintelligence. And it's way more useful to recognize that For example, in folding proteins, we're already at a stage of superintelligence, and in other things, we're not. And the arrival of AGI or even superintelligence doesn't change that, in my view. But the way in which it's really important is, I'd suggest, if another metaphor doesn't complicate it too much, I think of it as like cislunar space. Achieving AGI, or I'm sorry, achieving AGI or superintelligence is like being able to get into that area between the Earth and the Moon, where you've got a launch platform that isn't so restricted by the force of gravity. And now you can send missions to Mars and missions to Venus, et cetera, and start doing space mining and all kinds of stuff. So the LLM models have shown, I think, that if you could get, as you improve their levels of intelligence, then you can fine-tune them in the ways that are specific to this superintelligence aspect. Does that ring true to you, Nick and Dawn?
Yeah, definitely does to me. I think that's a beautiful analogy of how like the general capabilities of the model create a baseline that we operate off of, and we build off of those in specific subsets. So I think, yeah, from my perspective, the last year has shown huge improvements in their ability to, not require so much scaffolding and self-manage long horizon tasks and do planning and reasoning, and all of those things are incredibly useful core skills for doing task-specific work in the space.
Not requiring scaffolding is a down-to-earth way of describing my cislunar space thing.
Yeah. Well, that's a very engineering way of doing it, which is akin to
Stick
me.
with it.
Excellent. So they give me a list of questions. I have a personal question that I want you guys both to answer. The three of our talks and us three represent sort of three distinct spaces. So like my background's in industry, Dawn is from academia, and Richard, you're kind of from the government space. And a really potent question, and maybe I'll start with you, Richard, is when you think about the value add that your subspace brings to this problem of like cybersecurity and capabilities of these LLMs at defense and offense, what is it? Like, is it funding? Is it capacity to take long shots? Is it policy? Where do you think the advantages come from the government space at moving this forward for the nation or for humanity?
Well, I think government brings some capacity in places like DARPA, the national laboratories and the like. But I think it brings funding, and most of all, I think I wish the AI frontier labs and government would think jointly together more about the regulatory challenges. I think it's hugely attractive to say now, oh, we'll just go fast and unregulated is good. And I understand the arguments for that. But what I think is going to happen sooner or later is there's going to be a crisis. And it may be that there's some massive cyber attack. It may be that there's some misuse in other kinds of ways of AI systems. You can make up any number of scenarios. And when that happens, I think the move will be spasmodic and urgent, knee-jerk to intervene and regulate. It would be way better for us to think this out in advance and develop the relationship that we need between the government and the companies, and it's not as distant as at present.
Excellent. Dawn, do you maybe want to talk a little bit about like academia's contribution? Obviously, evals have come up a ton. Your work is extensive in the space. You have an incredible resume, but do you think about that as being the key value? Is there something more nuanced about academia that you think is really useful for this space?
I think that's a very good question. I mean, so certainly eval is an important contribution from academia, as we have discussed fairly extensively in this workshop. And I think there's even other contributions that I think academia is particularly well suited for as well. So in particular, when we talk about right in terms of future work, future directions, like academia is in particular well suited for things that are longer term, given the industry usually focus more on the shorter term. So for example, I think we have heard a lot of discussions about finding vulnerabilities and patching vulnerabilities and so on. So these, I would say, it's more in the near term, but how we can actually build, design, and develop these properly secure systems. Of course, this is longer term effort, but I think it's also really important for us to really, right, as my talk mentioned, to have AI to actually really help defenders. And in the past, of course, I think this paradigm has been very challenging, especially given the huge manual effort that's needed. But I do really hope that with the advancements in AI capabilities, it can actually really help automate a lot of these steps and efforts needed, and and hence so hopefully the these are I think these longer term thinking and approaches. I think academia is particularly well suited for carrying out. I mean, this is also why, if you look at a lot of the ideas, the early ideas, when they are still early, then it's more academia tends to play a bigger role, and then as later on, as the ideas become more mature, then industry actually can help doing the scaling part.
Nick, I want to ask you if I can, from an industry perspective, what's in my head is that, and I want to ask you if it's in yours or you think differently, is that there's a whole emerging force, which is the extraordinary proliferation of models behind corporate walls that are air-gapped or in other ways separated. And they're doing their own work, fine-tuning and developing models, so that there's a whole lot of stuff running around out there that will develop the field that is hard for us to grasp. And some of it, for example, in biotech, may be actually very challenging because it may run the risk of creating new viruses or things like that in ways that, though the frontier labs have been historically concerned about bioweaponry by malevolent actors, these are not malevolent actors, but we may be using AI in ways that we're not really as aware of as a society. What do you think about that?
Oh, yeah, that's a really great question. I think the answer probably lies somewhere in the blend. I do think there's a risk of organizations controlling the growth of a technology that has risk with it. But I also think that over the past 2 years, we maybe started on like a really strong foot. I mean, when some of the first work I ever started doing in the space was cyber evaluations for models. Obviously kicked off by the Biden executive order, but I think the space has started from maybe a more mature place than we typically do. While not regulated currently, I think the mentality across frontier labs and across the space is that risk of these models being abused is front of mind. I think the talks here are a great example, and maybe in a way that's maybe one of the more mature thought processes in the space. Is it's been discussed a lot. It continues to be discussed. I like the pivot now towards making the models useful for something other than offense, right? There's a fear that comes with trying to avoid something dangerous, and there's a control that you gain by pivoting over to, well, if the technology is really capable and some people are going to have access to it and maybe not necessarily be public about it, then the best thing we can get started in is like getting ahead of the defense problem. And I think that was very thematic for all of the sessions today, of people saying, knowing that they're going to be dangerous is something that we've actually thought of for a while, and it's maybe not super valuable beyond a certain point. But I agree with the risk. I'm just hopeful that the technology has mixed applicability to lots of spaces, and that we can grow in our ability to apply it to security strengths and defense faster than its risk on the offensive side.
And it obviously has immense rewards.
Yes, yeah. Maybe not unlike, vaccine development, and all the technology that goes into that to help prevent disease is bimodal with the dangerous aspects of building, bioweapons. I do not want to keep us over. I know we're maybe 5 minutes past, and they wanted us to keep the panel short, so maybe I'll yield out to final thoughts. But yeah, a second thank you to both of you too. Your talks were great, and I appreciate your insight.
Well, yours too, Nick. Thank you.
Thanks.
Great, thank you. Thanks a lot, everyone, for your great presentations and for the panel.
Thank you, Dawn, for rescuing my slides.
Yes, that was a clutch move for sure.
No, thanks for the great talks. Okay, great. Yeah, thanks everyone for joining such a wonderful workshop on frontier AI in cybersecurity, risks and opportunities. And this is again co-hosted by Berkeley RDI Center and Schmidt Sciences. And at the beginning of the workshop, we talked about why now that AI agents are reaching a breakthrough moment in cybersecurity. And I think this has been echoed over and over again throughout the workshop with the different speakers and so on. And given that we are reaching this pivotal moment, there are a number of key questions for us as a community to explore together, in particular, how we can have frontier AI to help more on the defense side versus the attack side, and how we can have the community, including academia, industry, civil society, and government, to work together to take the important steps, including we've heard about building more comprehensive evaluations, the RL training environments, and also for developing AI capabilities that can help more on the defense side, including building proposed secure systems and so on, to help the society to build up further resilience, in particular as the AI capabilities in cybersecurity reaching a tipping point. And with that, we want to welcome the community to join our efforts all together with building this Frontier AI Cybersecurity Observatory, both to further build out more comprehensive evaluations for AI in cybersecurity, as well as doing continuous monitoring of AI capabilities in cybersecurity. And also, we welcome the community to join us together for the following survey and to share your thoughts and voices about the development of AI capabilities in cybersecurity and also its potential impact in this space as well. And with that, we thank everyone for joining the workshop. For this part one, we have over 2,000 registered attendees. And as I mentioned, so we will also have a part two. So part two currently is postponed due to government shutdown that impacted a number of speakers for part two, and will be providing further updates once the government reopens for when part two will be scheduled. And also I wanted to quickly just share again, for people who are interested in learning more about agentic AI overall, please feel free to join our Agentic AI MOOC, Massive Open Online Course at agenticai-learning.org with over 32,000 enrolled in the series globally. And also, we welcome you to join the Agent Beats competition that just got started recently, with over $1 million in prizes and resources. And also there is a security and safety track for agentic AI. So we hope that the community can join us there. With that, thanks everyone. And thanks again for joining. And also, if you enjoyed the workshop, we hope that you can share more information about the workshop on social media and to your community members as well. Thank you.